sodium-ion batteries. And these are the few outlines relevant to this talk. First, the energy storage systems we are using at present, and then batteries, some fundamentals, and then later on the different types of batteries. Then particularly we are focusing on rechargeable batteries over here, and then the development of cathode material in these lithium-ion batteries and sodium-ion batteries, and further the applications of these batteries in various sectors. And later half, I have some research activities that we are doing in our laboratory lithium-ion battery PPU. And here I have taken the two cathode materials, one relevant to lithium-ion batteries and another one is on the sodium-ion batteries. So LiFePO4, this is one of the most prominent material nowadays in the industry as well as. So this is the material with itself with some modification and some you can say the composite I have shown. I will show the result over here. And thereafter we have NaCrO2. This is the first cathode material used in sodium-ion battery as a commercial material, and finally summary. So when we start with this energy storage systems, you know that we have many areas where we can store the energy. It could be the chemical or the electrochemical or electric means or mechanical means. And there are different ways by which we can we can store energy starting from batteries, the capacitor, the flywheel, or compressed air energy storage, and the thermal storage, and from hydropower. By all these means, we can store the energy. But nowadays, you see that the battery part is more prominent and it is increasing day by day. So let me start with the fundamental of the batteries. Usually, the battery in a cell, it is a device which converts chemical energy into the electrical means. So usually we have two types of battery systems, starting from primary, which are non-rechargeable, and these batteries basically are a different class of batteries, zinc carbon, alkaline, and we have AA, UAA, CND type, and the Jura cells. All these in the daily life we are using. These are the batteries. These are good in the part that they are disposable properly. Then we come to the second part, which are rechargeable batteries. And the primary batteries, basically, we can once charge and then finally it is discharged and disposed after that. So then secondary battery, you can go for multiple charge and discharge process. And the beginning of this battery system was from the lead acid, the nickel cadmium metal hydride, the lithium ion, and the electron. Lots of energy battery system nowadays you are hearing they are developing these days. So we have multiple charge oxidation reduction process in that, while in the primary we have a single reduction oxidation process. Once it is over, the battery is over. But in case of rechargeable batteries, so we call them secondary batteries as well. So we have multiple charge options. So when we see about the fundamental part of this battery system, we know that we have a cell reaction, and the two major parameters are there. One, we are having the kinematic parameters or kinetic parameter we call them, and another one is thermal parameter. Kinetic parameters actually these are basically the charge transport in the electron or ohmic voltage drop or mass transfer due to the diffusion or migrations. And the thermal parameter, these are enthalpies of the reactions, delta H frequency, and the gives energy, delta Z, and the entropy. So these are the relations which we actually hold over here for battery. And one thing is that this will decide how much a battery voltage will be developed. This is based on E naught is equal to minus delta G upon NF, where NF stands for total amount of battery charge, and this number of ions or electrons you can say simply multiplied by the Faraday constant. So the overall, it will be the potential V naught E, the equivalent potential, and we can get it, and that will be in the form of energy. So you know that the process in the battery is because of this oxidation reduction. So we have elemental over here different oxidation reduction processes, and all we take with reference to the hydrogen. All of us know about that. The positive side and the negative side for oxidation and reduction. So we can see accordingly that two are reducing agent from top to the bottom side, and the oxidizing agents from bottom to top side. Likewise, the vice versa. Then we see that the cathode, because we are discussing here about the cathode material, so we see the reaction in the half cell reaction. So with reference to this potential, we see the lithium itself. The lithium ion battery is a reference cathode as well. So it has minus 3.04 with reference to this hydrogen. And similarly, for the positive one like copper, oxygen, other molecules or atom will take. Accordingly, we will have. The basic thing is that the ideal battery characteristics when we take the cell voltage versus density, then it should be the green line. The ideal potential should be like that. But there are different losses or different polarizations, which actually you see the curve, you see it like this in this nature. So the polarization domination is in three reasons. We can say the first reason is due to the activation. This is the activation polarization, and because of the reaction rate losses, initial one. And the second plateau, it is because of the ohmic polarization, or we can say the resistance losses. And the third one, this is the mass transfer, which we say simply, and or the gas or mass transfer concentration polarization. So that we can see in these terms of cathode loss or membrane resistance loss or anode losses. So when we talk about the rechargeable batteries, we see in terms of volumetric and the gravimetric energy. So this actually graph shows you the lighter weight we are increasing. The light it should be lighter weight and the energy density should be high. Likewise, energy density. One is this is with reference to volumetric and this is with reference to gravimetric. Basically, we are taking with reference to size or with reference to weight. So accordingly, we see we start from lead acid batteries, so both are low. In that case, then further it was improved by nickel cadmium and nickel metal hydride, and then it was by the lithium ion or lithium polymer. And if we take the lithium metal itself, it is unsafe because we have granite formation I showed in the slides. So but we see the characteristic commonly used for the battery. When we see the lead acid batteries, we see the voltage, 2 volt over here. So this is a nominal voltage. And the nickel cadmium battery it is 1.2 volt, nickel metal hydride 1.2 volt, and nickel lithium ion battery it is 3.6 volt. So it is 3.6 volt particularly for the first lithium ion battery system which we have LiCu to lithium to hydroxide versus the carbon, graphite carbon. But it may change because of the material property. So then we have the specific energy density. Basically, it is 30 to 50. For lead it is poor, and for lithium ion, you can say it is higher. Likewise, you see the cycle life, the minimum 200 to 300 days of lead acid battery, and it is 1,000 to 2,000. Nowadays, more than that we have 5,000, 6,000, 7,000 operating systems, and the systems you are using like equations. So charge time, we say that it is minimal for the lithium ion, and the self-discharge is also less in case of lithium. So these actually characteristics make the lithium ion battery technology better as compared to the rechargeable battery system. So simply one term here we use capacity. The capacity is simply the charge might have been the formula which Q is equal to IT in the basic classes. So this is nothing but the I into T, the amp hour. It simply says the capacity of charge stored in the battery, and that we can read in this term what is multiplied by time to run in hours divided by the voltage. So why lithium-ion batteries? Already you have seen the many important properties that are better as compared to the rechargeable battery system. So lithium-ion here in this lithium-ion battery system, we have high energy density. They are lightweight. They have high cell voltage. They have flat discharge characteristics, low self-discharge, and very long cycle life as compared to the battery system. And we can operate minus 20 to 65 million. And nowadays, people are also trying to improve this range, lower side and higher side as well. And minimal memory fact and other thing is the small cell size. These all things make better this lithium-ion battery system good. So how this battery work actually, you can see over here, we have the working principle of this battery system. Usually we have charging discharging process as a cathode. We have, once you can see over here, this is the cathode material, oxide LiMO2. And the lithium part, some of the lithium part goes to the other side. Let's say this is the graphite card with the graphene layers. And here on the side we have the hexagonal material. So both are in 2D framework, the layered materials are here. So the lithium ion moves from us, it moves towards anode side. Similarly, in the other side, the electron through the circuit moves to the collector. Okay, and then after when we see the discharge process, then it is reverse of that. Like this. So this all thing happen in the presence of LiP6, this is the electrolytic medium, it is known as this. So this overall reactions we have in lithium ion batteries. And what are the components of the battery system over here? We have cathode, which is usually the metal oxide powder, and another one is anode, the graphite carbon, and many forms of the carbon other material also being used nowadays, and likewise the cathode also. So different class are there, I'll show you. So another one is the electrolytic material. It is a lithium salt opening solvent, and then we have separate which has micropores membrane, which is insulating, and particularly we use a polycarbonate. So these are the cell components of the lithium-ion batteries. There are two systems I'm showing here. The first one is the coin cell, the standard battery system we use over here also in our laboratory as well. And another one is the 18650. This is the standard for standard cell, and 18 stands for the diameter of this cell, and 650 is the length, and O stands for the cell, or coding have its meaning. And this is how we arrange our cathode and all the separator, all these things in the batteries of in the cylindrical battery system. When we see about this coin cells, they are very various standard to 2016, 2032, 2025, 35. Like this, many standard are there. So whatever suitable people use to do it depending upon the energy requirement as well. So we can see over here that we have a top, it is the negative terminal, and then we have cascade, then we have this spring to press it properly, and then we extend this spacious. And finally, these two are the basically the active, the negative active, that may be the lithium. With reference to that, usually we test the battery or the material basically, and then graphite, and then LTO. LTO is nowadays being used in the industry as well. So, and the separator, I tell you this is properly, and then positive electrode, this will be cathode, LFP, LMO, or anyone, or composite. And finally, we have bottom, which is the positive part. So, likewise, we have combination of this all component, and we fabricate a quantum battery. So, before starting to this cathode, let me tell you about this another problem which happens in lithium-ion battery, and the people are forced to come at the system which do not have much part of the lithium-ion battery, because lithium metal itself is very reactive. So, but it is good in terms of this specific charge capacity. We have 3,862 amp hour per kilogram, and in another way, the replacement we did with this graphite, which has 372 amp hour per gram. So approximately, you can consider 10 times we reduce the capacity. But why we reduce? Why we are doing this? Because we have to overcome with this dendrite formation problem, which is the cause of the blast in the battery. So we simply see over here that here we have lithium metal electrode, and this is your cathode, oxide cathode host. So what happens after a certain time when you have the lithium, simple lithium metal electrode, this dendrite formation takes place, and in between we have the separator. It actually penetrates the separator, the tiny contact is made over there, and that causes the thermal runaway in the battery. And after a few cycles, that's 100 cycles over here, that's given here, then we see that this thermal runaway, when it starts, the battery will blast. So to replace this dendrite formation, people use this structure, and that is the graphitic structure. Initially, it was started, but as I said you, that nowadays different MCMB mesocarbon microbeads are being also taken by industries. So this is the process. So simply, you know that still the lithium in this host, this is carbon, it has carbon itself is graphitic carbon itself have high capacity as compared to the cathode. So there's no problem. But when we are going beyond this capacity 372 for cathode, then it will be the problem. We cannot use this material. So how to calculate this capacity? Basically, here you can see with this reactions how this lithium ion moves towards the carbon graphene layers, between the graphene layers, and then we calculate the 372 milliamp hour per gram is coming for the anode. And likewise for cathode, these are the first material, first commercialized material by the Sony in 1990s. So it is 0.55. You can say the 50% of this lithium actually can move from 55% from the lithium to water side. This is the experimental data actually. Theoretically, when we calculate for whole, so we can say 150 milliamp hour per gram we can maximum get with this. So this 150 milliamp hour per gram is less than 372. So we can use this material as the cathode material, and we can use this carbon as a anode. So with the time, there is a development in the cathode materials. We can see that lithium-ion batteries have different type of cathodic material. So you see over here, this is the 2D material. So layer material we call it. Why we call it 2D? Because the lithium ion is distributed in a layer. These are the two-dimensional layer in CO6 tetrahedras. And another one is that olivine type, it is 1D, basically 1D framework, and different octahedra sites of MnO6, we can see that it lies over there. Similarly, the spiral structures, the FU and PO4, that are in octahedra are there in between. In between, this material is in 3D framework, but actually, if you see the layer, this layered structure is in 2D material. So, likewise, steroid kind of 1D material is there. So, these four classes, these are actually intercalating type of cathode material, which actually lithium ion moves inside the sites, and then finally it comes to come back to the cathode sites during this charge discharge process. So how this charge discharge process takes place and the capacity with different systems, you can see over here that we have the highest capacity with this NCM system over here, and even we have with some certain code. These are the binary or ternary material, but we also have the composites where we have the high capacity, and I'll show you in my slides as well. So this is the material which is also being used in the industry, which has high capacity, around 200 milliamp hour per amp. And then the first material, the lithium cobalt oxide. All the beauty of this material is that you can see we have a single plateau after that. But in case of Li-M2O4, you have a small the two plateaus where the voltage drop is there. So people use this is the drawback of that material, and the people try to drop this to make it a single plateau. And finally, it is done, but the capacity is reduced as compared to the pure you are getting. So another one is LIP FePO4. So this has a better quality as compared to this, so the flat discharge. So we can say the ohmic polarization is less in case of LiFePO4. Another class of this cathode material is conversion type. In that, the material go inside interstitial sites, basically, simply you are saying that. And in other side, we say that it is going on the surface of the lithium. So these are the conversion type of cathode, and they have high capacity. The research work is in progress in this material. But the drawback of this material is that they have multiple plateaus, and with the multiple plateaus, the potential drop will be different, and it is not you consider stable. So finally, what we see over here with this cathode and anode material in generalized form, that we have graphitic material. So for anode material, the potential should be as less as possible. So you can see the all anodic material, anode class is in the lower part of the potential around 1 to 2 range. And potential of your cathode should be high. You can see over here. So it is increasing. And there are certain material in intercalating class also, which we cannot test because of the restriction of your electrolytic material, which is not available more than 4.4, 4.5 volt. Because after that, the present material LiPF6 actually dissociates, and it blocks the intercalating sites. So this is that is why the people are nowadays using the solid electrolyte material, LNZO, and this all classes. So basic thing is that we have to improve this, and then we can get the high energy as compared to that. So we see the cyclic performance of this material. You can see over here that LiMn2O4 gives you it is the dark dots. When it is doped, with nickel and certain amount of lithium as well, at different sites, so you will see it has the stable cycles, and likewise the other material. So this is at the room temperature now, and when we increase the temperature, you can see the cyclability remains same. Only the change in the capacity is there with reference to the temperature. Similarly, other material, lithium cobalt oxide, you can see here. This is the cyclic performance, and here we use the different structure as Li, MnCO, and O2. This is another material which have the high capacity. So, like as you can see over here. So these are the different material classes where we know starting from the layer, the spinel, the olivine, and the telluride. So what are the materials which are commercialized, or how much voltage they can provide? These all parameters are here. So we simply say this LiTS2 actually it was the first material for which it was granted the Nobel Prize as well to MS Bittingham, who gave the concept with this material, and then later on lithium cobalt oxide was developed by uh, be good enough from Texas Austin. And he also brought and for the graphitic material as an anode to Akira also brought another price for this. So these are the material basically which can be commercialized. What are the key requirements of material to be cathode material for a charging battery? Because since we are focusing on this, you say the cathode material, so what should be there? How we decide that this material can be used as cathode? So these are the few points that we have to understand that the material contains a readily reducible oxidizing ion, and particularly in that case, we have the transition metals. So you will see in the formula lots of transition metals are there. Another one may be the materials react with lithium in reversible manner, so that it should have good reversible property, and it should be integrating type, keeping host unchanged. The structure should be stable; it should not change. Metal react with lithium with the high free energy of reactions that will decide its potential. And this is basically delta G we are talking. It should be high, so you get the high storage potential, high capacity. Metal should be a good electronic conductor. It will allow easy addition or removal of electrons. And if the material should be stable, then the structural change will not be there, so we will have good cycling performance. So these are the properties. And another main thing is the metal should be cost effective and environmental friendly. So what are the factors influencing the performance of lithium-ion batteries? Well, in one factor, you can see the reactions where by which we have delta G is equal to U naught and F. U naught is nothing is E naught actually. The symbol is changed over here. So the reaction occurring at the cell should be high. So there should be high energy. If it is low, basically potential will be low. So that will influence. What should be the capable acquiring higher lithium ions, and they have a good electronic conductor. They should be stable over wide range of voltage. They should be minimum force modification while you can certain exception, because the volume expansion problem is there in the carbon as well. So the people are replacing it. So there should be less modification in this factor. So this factor will influence. Another factor is the stability window of electrolyte should be wider. As I tell you that there are certain materials we could not test them because of the limitation of electrolyte. So if the window is higher, then that factor will also influence the performance. Another thing is the charging potential of cathode. It should be high. As it is high, then the difference with the anode will be high, and you will get the high energy density as well as the power density. So now the discharging potential of anode that should be low, so that the delta we should more or large. What are the challenges and issues with RIVs? So main issue is the safety. These are hazardous toxic due to their flammable electrolytes, and if damaged or incorrectly charged, then it can lead to explosion. As already you have seen, the Samsung was forced to recall this Galaxy Note 5, Galaxy Note 7 handset for lithium-ion batteries. And there need to specific environment and conditions to fabricate LIDs because you require at least Earth atmosphere to level of where your oxygen and moisture, you can say H2O molecules should be less than 0.1 ppm. So that environment is required, particularly blocks with that environment level is required. Recycling is a major issue with this battery system. Still, it is actually issue. People are working on that, and the developed countries are giving nowadays a project basically on the cyclability of lithium batteries. Why? Because you can reuse the material, and other thing is the lithium resources are limited, and unfortunately in India recently you have used that in Jammu and Kashmir for the lithium resources. So that may be good for us, but again it is limited throughout the world. So alternative to lithium-ion batteries, people are working nowadays on sodium-ion batteries and another magnesium-ion batteries, aluminum-ion batteries. Also, battery system are there, but the comfortable one we say that the stable one that sodium-ion battery system. And SIVs again these are rechargeable like LIVs, lithium-ion batteries, and these batteries are basically recently started work on this battery system, so we can say these are young. So battery grade salt of sodium are cheap as and they are abundant, and they are much more than the lithium ions, the lithium metals rather. And attempts of SIVs are undertaken actually 96 by 4 motors, and they made that time the sodium sulfur battery. Actually, it requires a high temperature, so that people are trying to do at room temperature as well. So this system as well. Then the factor like price, evidence, size make them interesting, particularly for large scale storage implementation. And the raw material is 1,000 times cheaper and the lithium as compared to lithium or sodium, and they are safer as well, and they have great promises for largest energy storage in general. What are the disadvantages of these battery systems? Sodium ion is 30% large as compared to lithium and diameter, you can see, and the two times heavier. So that will be there. The energy density problem is there because the same energy density you cannot get. If you will get, you require more number of cell combination of the cells, and that will actually increase the weight as well, weight and size both. So large ionic size of sodium ion, which requires more power to keep energy flowing, and it takes several hours because to charge in case of its fully discharged states. They have lower operating voltage, because you know that in case of lithium ion we are having 3.4 to 3.8. Now this is normally I'm talking, but open circuit is more than 4.2, 4.3, 4.1 likewise. But in that case, the operating voltage is around 2.7. So you can see that that is less. So low energy density is also the problem with this. So ionic form, you can see the size in reference to it here. What are the number of cathodes for sodium-ion batteries? In sodium-ion batteries, we have NaCl2, this is a layer type of sites, and NaFeO2, and this is the material which is commercialized as well by a few companies. And polyanion compounds, another class is polyanion compounds. These are the phosphates. In phosphates, we have orthophosphates, paraphosphates, fluorophosphates, silicates, sulfates, and mixed polyanions. And the third class of this material is Persian blue analogs, PBAs, we use as the cathode material for sodium ion batteries. So when we compare these two battery systems, usually we have the ionic radius size, the small radius size, which is beneficial for lithium ion. But again, the problem of the thermal stability is high as compared to sodium ion in case of in case of lithium ion batteries. So that is why we are replacing this. We are replacing, or we can say we are substitute for that. Gravimetric capacity is also low. All parameters are less as compared to the lithium ion you see. And these are the basically the systems or the cathode and anode materials and the coordination preference of the cells over here for lithium and sodium. What are the applications? All of us know that nowadays these dischargeable batteries are being used from starting from a very small devices to a large system. So very small batteries we can use we are using in medical implants, RF transmitters, hearing aids, and small batteries, particularly in cell phones, digital camera, laptop, portable, and all these military applications and scientific applications. And large battery system that we are using in the electrical vehicles, the car battery, the industries, and large scale stationary applications. So lots of applications are there because all renewable energy which we are developing that we have to store in this battery. So these are the few electrical vehicles classes which we have developed till now. So we can see the HEVs which are already in the market for different companies, and we have PHE plug-in hybrid electric vehicle, purely electric vehicle, and FCH with the fuel cell based electric vehicles. So these are developed under development by the all companies. And now I'm showing you the research work which is performed in LIVT lab, in our lab. So what are the area of interest? The work is going on in the cathode and anode materials for lithium-ion batteries and the sodium-ion batteries, and the solid-state electrolyte for LIVs, SIVs, and solid-state batteries, supercapacitor material. And final aim is to we are testing material with the coin cell, but the aim is to fabricate prismatic cells with these sort of materials. So these are the facilities, glow box workstations in our laboratory, crimping machines for the coin cells, and multi-channel battery testers, the rolling machines, and this is the coating unit, and electrospinning unit. So the slide show you the few results quickly for the developed in our laboratory. This work was done by my PhD student Rakesh Saruha. So development of zinc oxide, basically zinc oxide of uh, LiFeP4 we prepare, and then we prepare the dual composite for this. So this was the synthesis parameter. We use the salt gel method over here in that, and we initially took all the stoichiometric, uh, all the precursor and the stoichiometric amount of that is used. Finally, DI water is used as a curating agent, and the gel formation was done. The dried, all the steps were followed, and finally we got the material after this calcination, and then characterization were done. So with the characterization, what it is observed that we synthesize zinc oxide ourselves as well in the laboratory, and then LFP, and further the different weight proportion of this zinc oxide were docked in 1%, 2.5%, or 5% or mix. And what we observe that the proper phase is formed, it is a orthorhombic phase of of LFP and with PNM space growth. So what we see here, the no extra peak was found, which shows that there is a morphic carbon. So it shows the carbon is morphic in this. And another one is that the zinc oxide peak is also not there separately. So we see that it is gone inside the host lattice. The work was published in the Applied Surface Science. So when we observe the AC and DC connectivities, the data was taken in 20 Hz to 1 megahertz range. And what we observe that the electronic conductivity actually it increases 10 to 3 times, and it is best for this 2.5% of zinc oxide drop. And similarly, the ionic conductivity we can have over here. So with this reference, we found that the minimum activation energy. This is the data is observed for EIS, electrochemical impedance spectroscopy, and that also shows that the battery we observe this 2.5. And then cyclic voltammetric performance was done. So it corresponds to two phases. You see the reactions between Fe3 plus, this is Fe4 and Fe2 plus, the oxidation reduction process taking place. And with that, we found that it is observed the best one for again for LFPZ 2.5. So gravimetric analysis we also did, and we found that it is around 160 to 163 milliamp per gram is observed experimentally, and for this optimized system, LFPZ 2.5. And you know the theoretical capacity of this material is 170 milliamp per gram. So you can say it is a very good result in reference to the theoretical capacity. So this is the first cycle data. Similarly, we did the rate performance, and in the rate performance, different rates it was discharged, 0.1C, 0.5C, 1C, 2C, up to 5C we discharge it, and again then put 1C. So what we see there is no change in the capacity we observed initially. So it is same. And then we did the cyclic analysis. So you can see it is by and large constant and higher for LFPZ 2.5. So the rate capability, the diagram plot we did, how much power flow versus energy density. So with the highest rate, we can hold it up to 6.3 minutes for the drop sample, and for pure sample LFP, it was 1.02 minutes. So after different cycles, after 50 cycles, what we did, we also did the postmortem. We opened the cell, this one to the cell, and you want to see the structure that what is the change in the material property. This is by and large, it is before the cell fabrication. This one is raw powder, and this is after that. So by and large, same material properties also in that molecule is the same after 50 cycles. So this was one of the material. Then we tried with this combination of allied terminology, which is again a class of layered material. But the problem with this material, we cannot utilize, we could not utilize rather the full potential of that because its potential is around 4.6, 1.8, 4.7, 4.8 around. So our limitation because of this electrolyte is that we can achieve up to only 4.5 around. So the two classes we prepared over here, two classes of cathode were prepared. One cathode where we are mixing with these different ratios. LFE 1:3, LMO 1:1. LFE and LMO ratios are there. 1:3, 1:2, and 3:1. Another, we did this layering phenomena. Initially, we caught our material that is let's say LFP on electrode, and then we got LFP. So double layer gas structure LFP on the bottom in the contact with the aluminum current collector, and another one is layer allied to aluminum. So this was the combination AL. This is AL. AL is aluminum sheet. Over that LFP is coated, and then after LM was coated. So what are the results for the first one? You can see that LMO. This is a layered material, so perfect layered material is received. attain, and then LFP, which is also the orthogonal structure. When we did the charge discharge process, you can see the capacity is increased around 208 milliampere per gram at a rate of 10 milliampere per gram current density. This is the combinations which we are using for 1:3, 1:1, 3:1. Similarly, for the another arrangement, what we did with this two combinations of LFP and LMO. So what we observed, 208 again with this. So it was at the 10 milliampere per gram. Now we come to the another materials for this sodium ion batteries. The work was done by Abhishek Bhargava, who was some thesis, and on sodium ion batteries, development of sodium ion batteries. So in this work, what we did, we have different compounds of chromium and sodium carbonate, the oxides, and effectively we made it in argon atmosphere, and then it was taken to tubular furnace for 90 heated, and what we got NaClO2, and this was further exposed to C2S2 and S2 atmosphere at 750 degrees Celsius. So what we found that the core cell, it is not exactly core cell if you see the data, core cell like structure I can say that way. So this nature was observed. So this is the XRD pattern where what we did, this is NC0 stands for your pure sample of NaClO2, NC5 the 5 node exposure of C2S2, and 10 node exposure and 50 node exposure. So in that, what we also, these all are the structural analysis done by Ritfield. So what we observe that, you can see that these are the FESEM images of NC0. We have observe the structures of the crystalline structure, and you can see the morphology is a bit dense and spherical type, not exactly spherical. So according to that, the 5 minute exposure, this is pure, this one is 5 minutes, then 10 minutes, and then 15 minutes. For this, you will see the particle size is also changed in that. These are the TM images of all. So here, this is pure one, and then 5 minute exposure, then 10 minute exposure, and then so graphene like the structure we observe that it is not uniform. That is why I tell it is not perfectly the core cell, but like core cell like structure we observe to each particle. So with that, what was the change in the capacity of the parameter? And so we observe over here that 3.01 volt, 001 volt. This is the output voltage for that oxidation reduction diagram for CV. And here we observe this delta V, the polarization is just 0.095 in case of 10 meter exposure of C2S2. The capacity observed, this is the for raw material, it is around 70, 72, 73 milliampere per gram. And for this material, if you optimize it, is around 27, 26 milliampere per gram. So with this data, we can see that this is improved with this exposure of acetylene and the carbon deposed in the form of graphite carbon. Gate cavity were also tested, and here we observe that 0.1 C and 0.15 C and higher rates, and then finally it drops, and 0.1 C again it is observed the similar. So here you can see the sluggish behavior of sodium ion, as we see that it requires high energy. So that initially it should be the down, but initially it should increase because we get efficient kinetic energy with this high rate, and then it drops. This is the cyclic number data for 40 cyclic were tested. We see it is by and large the same. Then we did the EIS. The EIS analysis also shows that the conductivity and all this improvement, and the RCT, the charge transfer resistance, also low in Nsut, and the diffusion coefficient we observe, this is also high in case of Nsut sample. So finally, we tested with this radon plot. So here we can see that highest C rate we tested over here, it is 2C, because at 5C it is not observed in the pure NCR material. And in case of NCRO2 with the 10-second exposure of C2S2, at least 8 seconds we observe for the highest 5 CJ. So this is the parameter that how much less we can hold. And after charging discharging, we see that the dynamite formation also observed in case of the sodium ion batteries. So here, this is for the pure sample. Pure sample means NaClO2. After after 50 cycles, you see the dendrites is formed in that. And this one is where the coated one. So structure is hardly changed. So only the modification, or you can say the mixing that nature observed in case of Nsut sample. Thank you. This is all about my side. These are my students. Some have completed PhD and some have submitted these two, and some are working. Thank you very much. Any question? Hello.
Thank you so much, sir. A big round of applause for sir. Sir, it was a pleasure listening to your talk, and it would have been our privilege if you could have come in offline mode and we could have interacted with you. So I will now take any questions from the audience and the online participants. They can also unmute yourself. You can also unmute yourself if you want to ask any question. Yes, sir. Sir, we have one question.
Yeah, please. What is the role of
Solid electrolyte interface.
solid electrolyte interface? When we start initially the charging actually to any material, new material, to start to make over there, this solid electrolyte interface actually make the passes to the ion, lithium ion or sodium ion, whatever it is there. And it also, the two way it works, one it is the passage, another one it is also restrictive. When the structure is not stabilized, then it is in the restrictive way, it works to oppose the movement of ion as well.
Okay, sir. Sir, I have one question. In the slide that you showed about postmortem SEM, A and B images correspond to the same material before and after
Yeah,
cycling.
this you are talking or lithium ion or
Yes, sir.
sodium ion?
Sir, this one.
Okay,
So,
yeah,
like, we
this
can
is,
see that there is a drastic difference in the morphology. What could be the possible reason for it, sir?
I'm saying that the dendrite formation, these are the dendrite actually. This is the needle like domains you see over here. These is the dendrite formation. This is the pure material. When we coat it, there is no dendrite formation.
Yes, sir.
Okay, so because of that, the dendrite formation, what happens? It makes panic contact, so internal resistance will increase in that also. And also it generates the thermal run in these battery systems.
Okay, sir. Thank you, sir. Any other question? So, thank you, sir, once again for your informative talk. Informative talk.
Okay, okay, thank you.
Thank,
Okay.
thank you, sir. Now, I would like to give a brief introduction to our session chair, Professor Dhiraj Kumar Singh. Sir is working in IIT RAM Ahmedabad, and Sir has been awarded the very prestigious Alexander von Humboldt Fellowship of Germany. Sir has also been a JSPS fellow in Japan and was also awarded the DS Kothari Postdoc Fellowship, which is awarded by UGC. So Sir is handling DST Sir projects which amount to more than 50 lakhs, and his areas of research include functionalized nanomaterials, frequency and time domain spectroscopy, Raman UV visible fluorescence, quantum chemical calculations, ionic liquids, biomolecules, and molecular interactions. Sir has more than 72 publications in international journals of repute and has published more than 4 books. So with this, I would like to invite Dheeraj sir to session the chair. Thank you.
Thank you for the introducing me. Now, in this section, there would be one invited talk and 5 online oral presentation. The first invited talk is from Dr. Salesh Sharma. Now I would like to introduce about the Dr. Salesh Sharma sir. Dr. Salesh Sharma sir is Senior Principal Scientist in CSIR NPL and Professor in ACSIR. Research interest is colloidal semiconductor, quantum dot and nanoparticle for optoelectronic and photocatalysis biosensing application. More than 14 PhD students has been completed his PhD under his guidance, and six PhD students are pursuing their PhD. 30 MTech and MSc dissertation has been completed under his guidance. His H index is 30, and he has published more than 200 publications in reputed journals. And he is also coordinator of coursework in the area of advanced semiconductor devices. So he will present the work on his water treatment research. So I would like to welcome Professor Salesh sir. Please.
Yes.
So, thank you, Chairman, for your kind introduction. Today, first of all, I would like to thank the organizers of NSUT for giving me the chance to present my work on this platform. And the topic of my presentation today is sustainable and visible light driven, low cost, photocatalyst based on multi-component chalcopyrides for wastewater remediation, and this work I had been carrying out in CSI NPL. So this is my brief profile. Already introduction has been given, so no need for this one. So first of all, we would say that what are the humanity's top 10 problems for the next 50 years? And we know that energy is the foremost, followed by water, food, environment, poverty, terrorism and war, disease, education, democracy and population. So water is the most important. So energy and water are the two foremost problems which the humanity will be facing in the next 50 years. And for that, we have to see that what type of nanocrystals, whether it is chalcopyrite semiconductor nanocrystals, CIGS or CZTS related nanocrystals can be used for the water remediation process. So before going on to CZTS, I would like to start with a brief introduction to CIGS and nanocrystals. Basically, CIGS is copper, indium, gallium, selenide, diselenide, along with a sulfur component. And they are produced by two processes. First is the non-vacuum process, and second is the PVD, that is physical vapor deposition process. Now the non-vacuum process is by chemical route, electrodeposition, spray pyrolysis. The advantages are uniform deposition, high materials utilization and low cost. And the cost reduction is less than $1 per watt. Whereas the physical vapor deposition includes co-evaporation, sputtering, PLD, but the limitations are that they are expensive, low materials utilization. So what are the critical issues in the use of CIGS semiconductor nanocrystallites? Particularly, the issues are related with the interfaces, the moisture problem, the structure columnar films which are deposited by alternate processes. The absorber layers have to be less than 1 micron thickness. And moreover, the most important is the CIGS film stoichiometry and uniformity over large areas. And the sustainability of materials like gallium and indium, that plays a very important role for these nanocrystallites. Therefore, we have to switch over to earth abundant elements like zinc and tin in order to replace the CIGS nanocrystallites. But as we know that CIGS nanocrystallites enjoys a very high cell efficiency of around 23%, and they are known as order defect compounds, means all the defects are typically in a ordered manner, and therefore the grain boundaries doesn't contribute much to the deterioration of the device. And another leak is the copper zinc tin sulfur selenide, that is CZT-SSC, which is a characteristic similar to CIG-SE, a potential replacement for CIG-SSC light absorber in thin film photovoltaics. It is alternative for the replacement of expensive and scarce element, that is indium, in CIGS by much cheaper and earth-abundant elements like zinc and tin. It replaces half of the indium atoms by zinc and other half by tin. Excellent photovoltaic material, that is the non-vacuum process CZT-SSC efficiency is close to 13.6%, which has been reported by IBM USA, and which is higher than the vacuum processed efficiency of around 9%. And not much significant work has been done in India. It has a direct and variable band gap ranging from 0.9 to 1.6 eV, and it has a large absorption coefficient more than 10⁴ per centimeter and low toxicity. So for the synthesis of these CIGS or CZTS nanocrystallites, we opt for colloidal quantum dots or colloidal nanoparticles, which is a non-vacuum technique. Basically, colloidal quantum dot synthesis is a colloidal chemistry which is very simple, cheap and fast. And here the film deposition is by spin coating, where the colloidal quantum dots are suspended in organic solvents. Multiple advantages are that there is no lattice matching of colloidal quantum dots and the substrate, no limitations on materials combinations, near ambient conditions, large area deposition, multiple exciton generation, and access to infrared wavelengths. So if you see the graph between the quantum dot diameter and the emission wavelength, if you start from CDS and you go to PBSE, you can tune over a large wavelength, right from IR region up to the visible region, so say UV region to far IR region, we can go from CDS to lead selenide just by varying the different types of nanoparticles. And there are two techniques of preparation. One is the hot injection technique, which is the most common and the most popular technique. And another is the rapid injection process, that is the rapid technique, heat process. In the hot injection process, basically, it is being produced by using a highly supersaturated condition by the rapid injection of excess of precursors into a hot surfactant solution, resulting in the nucleation process because it relieves the excess, gives free energy of the system or the saturation. And during the nucleation process, the monomer concentration, which are the building blocks of the nanocrystallites, they decrease in the solution and thus nucleation rate slows down. So basically the aim is to separate the nucleation and the growth process of nanocrystals in order to achieve the similar sized nanoparticles, that is the monodispersity. And it is carried out at a temperature between 250 to 300 degrees centigrade. So the work in CSI NPL on the water remediation using colloidal CZTS nanocrystals. So as I said, we can prepare these nanocrystals by using hot injection technique. And as I had already given the introduction to CZT-SSE nanocrystallites, which are the quaternary chalcopyrite compounds, which belongs to 1, 2, 4, 6 compound semiconductors and has got unique properties like high absorption coefficient, direct band gap of 1.4 to 1.7 eV. They are earth abundant, low cost and non-toxic. And the objective of this work was to effectively degrade the organic pollutants, the textile effluents which are present in water. That is, the organic pollutants are sodium, chloride and sulfide salts, and the pesticides and the insecticides. Whereas the textile effluents are the dyes, volatile organic compounds, and we have to get rid of these organic pollutants and textile effluents during wastewater treatment by using our CZT-SSE nanocrystallites-based photocatalyst. As I said, the main advantage of CZTS is that it can be prepared by non-vacuum technique with ease of band gap tunability and controlled size growth, including different morphologies. The synthesis procedure, as I said, it's by hot injection technique, where we have used two sets of nanocrystallites, that is CZTS1 and CZTS2, using trioctyl phosphine oxide and trioctyl phosphine as ligands, and another set of nanocrystallites includes butylamine and octadecene as ligands. We prepare it by hot injection technique, And initially, the nanocrystallites to start with are hydrophobic, and since we will be using it for water remediation, so it's very important to make this hydrophobic nanocrystallites into hydrophilic, and that we can do it by ligand exchange process. So we have to do a ligand exchange process with the help of L-cysteine, so that all our hydrophobic nanocrystallites are converted into hydrophilic, and we can use it for water remediation process. This is the typical characterization XRD, and as we can see, there are two sets of nanocrystals. That is, one is with butylamine octadecene mixture, and another is with topo-top mixture. So before ligand exchange, we get typical casterite peaks, and after ligand exchange, we get the wurtzite phase, which is more stable, particularly for the photocatalysis purposes. And there is no impurity, there is hardly any impurity peaks observed during the phase change, and the peak pattern shows high crystallinity of the nanoparticles, and the ligand exchange process results from casterite to wurtzite is seen because of stress and strain which is caused during the procedure from when you make it from hydrophobic to hydrophilic. The Raman spectroscopy is another tool through which you can find out whether there is any impurity phases or not. So both for CZTS nanocrystallites, say with topo-top mixtures and with octadecene and butylamine mixture, there was no presence of any impurity, binary or ternary phases in the nanocrystallites, and we can claim that our nanocrystallites were quite pure. This is the UV visible spectra before and after ligand exchange for both set of nanocrystallites with topo-top mixture and with butylamine octadecene mixture. And before and after ligand exchange, the band gap lies in the visible range, and in fact the band gap after ligand exchange for topo-top mixture changes from 1.63 eV to 1.50 EV because of the increase in dimensions of the nanocrystallites, and it is very obvious because once you remove the ligands from the top of the nanocrystallites, this nanocrystallite size increases. Similarly, for the set of ligands from butylamine and octadecene mixture, there is a change in the band gap from 1.75 EV to 1.54 EV. So in both the cases of nanocrystallites after ligand exchange, we have the band gap in the visible range, and it can be very well used for the photovoltaics and other photonic applications. These are the transmission electron microscopy pictures, where in CZTS1, which is for topo-top mixtures, we get a set of nanospheres and nanorods which are highly crystalline, and they are agglomerated nanorods of 120 to 140 nanometer dimensions, and nanospheres are of 20 to 40 nanometer dimensions. And for CZTS2, which is butylamine and octadecene mixture, again we get nanospheres which are smaller in size, that is around 2 to 5 nanometer particles. Nanoparticles are observed with a fringe width of 0.2 to 0.4 nanometer. And high crystallinity is evident from the selected area diffraction pattern. And the second one shows the diffuse rings in the selected area diffraction pattern, which is evident because of the small nanometric dimensions of the nanocrystallites. This is the dynamic light scattering, which is used for the calculation of the size of the nanocrystallites for CZTS1 and CZTS2. Here I have to say that this size is not the accurate size of the nanocrystallites, because DLS never gives you the accurate size. Basically, it gives you the hydrodynamic size. And the hydrodynamic size includes not only the nanoparticle, but also includes the ambience around it, the ligands surrounding it, and therefore the particle size which is estimated from DLS is always more than the actual particle size. So one should always go for the transmission electron microscopic studies in order to observe the accurate particle size for TM, but it does give you an idea about the particle size for different types of nanocrystallites, and particularly whether it is monodispersive or polydispersity, and that is very important. So as you can see in the inset of both the figures, that the polydispersity index for CZTS1 and CZTS2 before and after ligand exchange, it is less than 1. So it is between 0.5 to 1, and therefore it is monodisperse, and therefore we can safely use it for our photocatalysis purposes. The contact angle studies are there. So if people are aware that contact angle is normally used to show the wettability of a particular nanocrystallite. So if the contact angle is more than 90 degree, then it is hydrophobic, that is water repellent, and if it is less than 90 degree, then it is hydrophilic, that is water loving. So since we have to use these nanocrystallites for water remediation process, it is very important that after ligand exchange, we measure the contact angle, and we have seen that the contact angle before ligand exchange is quite high, that is in a typically hydrophobic range, but after ligand exchange, it comes to 106.28 degree. Similarly, 41.33 degree from very high contact angle, and similarly from 106.28 degree to 18.31 degree. So it becomes super hydrophilic, means these nanocrystallites can be easily used for the water remediation process. Then these FTIR studies were done to find out that after ligand exchange whether the PO bonds, which is a characteristic of topotop, are being replaced by the amine ligands, since we are treating it with L-cysteine, and we have seen that there is a PO bonds reduces with ligand exchange, and more amine related groups are incorporated in the nanocrystallites. So one can easily say that after ligand exchange, our crystallites have become fully hydrophilic, and it can be used for photocatalysis purposes. Now, the photocatalysis experiments were performed under two conditions. The first condition was the bare sunlight, where the intensity was maintained at around 900 watt per meter square. And the second one was focusing the sample using a converging lens, which increased the intensity of the light to 1800 watt per meter square. It's almost the double as compared to the bare sunlight. And once you increase the intensity of the light falling on the sample, then the photocatalysis mechanisms becomes faster and more efficient, because the converging lens will increase the photon flux on the sample, and therefore your exciton generation will, large number of exciton generation will take place, more electrons and holes will be generated, which will attack the water molecules to produce oxygen, hydroxyl free radicals, which will react further with pollutants and impurities to convert them into oxygen, hydrogen, carbon dioxide, and other harmless products, including organic, inorganic minerals or acids. And the photocatalytic efficiencies, with the help of converging lens, although there was not much difference in the photocatalytic efficiency, it is around 98.4% from 98.1%, but most importantly, the rate of degradation improved a lot, from 0.04 per minute to 0.14 per minute. That is the time taken where the dyes used to degrade from, say, it used to take around 90 minutes for the complete degradation of the dyes. With the help of converging lens, the same phenomena was occurring within 30 minutes. And basically, why we have used the dyes, as I said in the beginning, that we are focusing on organic pollutants and textile effluents. And these organic pollutants, for reference, we have used methylene blue as a typical reference. And for the textile effluents, we have used mixture of dyes like methyl orange, malachite green, Congo red, mixed in a typical ratio, so that the unit absorbance is observed, and that we take it as a reference for the textile waste, and CZTS and its related compounds we take as a photocatalyst. So as I said, basically the photocatalysis involves the photon absorption followed by electron and hole generation, where the CZTS, after reacting with the electrons and holes, it leads to oxidation and reduction processes, yielding oxygen radicals and hydrogen radicals, and there is a charge separation which helps in the photocatalysis mechanism. So as we see on the right hand side, that they are CZTS1 in sunlight, organic pollutants, that is without lens, and this the time of degradation, because we have to monitor the absorbance of the dyes. So the dyes degradation continues with the increase in the exposure of the photocatalyst in the presence of sunlight, that is from 0 to 160 minutes, complete degradation of the dyes are observed, which gets accelerated when we use a converging lens. The time taken is only 60 minutes as compared to 160 minutes. And the photocatalytic efficiency, although it remains the same, but the degradation rate constant improves a lot, from 0.014 per minute to 0.04 per minute. So that's the improvement in the degradation constant. Similarly, for another set of nanocrystallites which were prepared by butylamine and octadecene mixture, the organic pollutants, there was a change in the degradation rate from 0.04 per minute to 0.14 per minute, although the rate of degradation efficiency almost remains the same with the use of organic pollutants, particularly for converging lens. And for the textile effluents, we want to increase the rate of degradation efficiency. The degradation efficiency is 75%, which is slightly less as compared to 98 and 99% degradation efficiency, which we normally observe for organic pollutants. But the rate of efficiency was good enough. That is, we could easily, increase the rate of degradation constant, and the rate of degradation improved to 0.03 per minute as compared to direct CZTS2 nanocrystallites without using any lens. And to check the reproducibility of our nanocrystallites, we checked it for a different number of cycles. Up to 25 number of cycles we have carried on this photocatalysis process, and the materials were found to be highly reproducible and repeatedly tested for 25 cycles. And these CZTS nanoparticles will effectively maintain the degradation efficiency with only 3 to 5% loss. And the sample allocates at different time intervals are also shown in figure, showing the color degradation of the water pollutant using methyl green, and for RH, malachite green, and the rhodamine. And from these different cycles, we can conclude that easily one can go for the higher cycles, as I will show in the subsequent slides. Then we can go to a higher cycles, even up to 45 number of cycles using these nanocrystallites. So these are the different, it's a table comparing the efficiencies and degradation constants with the time taken by the different CZTS with different pollutants. It's a comparison of our previously reported data and the present work along with the literature survey. And as we can see, the bold highlighted part denotes our work which has been carried out in CSIR NPL, and we can see the improvement in the degradation time constant up to 60 minutes and 30 minutes for CZTS2 nanocrystallites, and for CZTS2 with butylamine and octadecene mixture, the whole process can be carried out in 50 minutes. So there is an improvement in the degradation time constant and the degradation efficiencies when we use the converging lens. Then another set of compounds which we use is CZT-SSC, which is a multi-component chalcopyrite. Earlier we were using CZTS. Now we have included a selenium component along with it, which improves its photocatalytic and charge separation efficiencies. Now the CZTS-E is same as CZTS. It has a high absorption coefficient, direct band gap, earth abundant, and non-toxic. And we have synthesized a series of CZTS related compounds with different concentration of selenium and sulfur to study the effectiveness and fast charge transfer rate during the photocatalysis. And therefore, as compared to CZTS nanocrystallites, again we have done the ligand exchange with L-cysteine because we have to convert the hydrophobic ligands into hydrophilic because we are using it for water remediation. These are the X-ray diffraction pattern of CZTS and CZT-SSC compounds at different ratios of sulfur and selenium. And the most noteworthy important thing is that here for the stoichiometric CZT-SSC, where sulfur and selenium ratio is 1:1, we get a perfect crystalline properties with no presence of any impurity, binary or ternary phases, which are seen for other ratios. So it is one of the most, not only the input ratio, even the output ratio yields stoichiometrics, sulfur and selenium, and therefore we can safely say that there are no binary or ternary phases. These are the different absorbance studies recorded of these nanocrystallites. The band gap of these CZT-SSC based systems varied from 1.82 eV for CZTS up to 1.37 eV for CZTSE, and in between we have different ratios of sulfur and selenium. So all basically lies in the visible range. And here we observe that a nanocrystal size increases with the selenium content, where there is a decrease in the band gap value, and this is because of the fact that a sulfur atom have a small atomic diameter or around 0.18 nanometer, and it is being replaced by larger selenium atoms, which is 0.1 nanometer in the lattice, and there is an increase in the size and therefore decrease in the band gap values. The hydrodynamic diameter from DLS experiments were calculated and were found to be around 789 nanometer, 940 nanometer, 1056 nanometer, 1216 nanometer and 131 nanometer, corresponding to different concentrations of sulfur and selenium. But the most important point is that the polydispersity index lies between 0.1 to 0.5, that is all these nanocrystallites are highly monodispersive. Then electrochemical studies were done. And from the electrochemical studies, we have see from the Nyquist plot, we can see that the minimum charge transfer resistance was observed for stoichiometric CZT SSE, where sulfur and selenium was maintained at 1:1 ratio. And that shows the importance of our compounds. And therefore, typically, as we have seen that the contact angle before and after ligand exchange, so before ligand exchange, the contact angle is quite high, 146.55, which shows the hydrophobic nature of our nanocrystallites, but after ligand exchange with L-cysteine, the contact angle decreases to 8.66, which represents hydrophilicity of our nanoparticles. These are the transmission electron microscopic crystals results where we have used the crystallinity, and here we get typical nanorods. So in case of CZTS, we used to have a mixture of nanorods and nanospheres, and in the case of CZT SSE, we get typically nanorods. And the average size of the nanorods is between 155 to 170 nanometer, and it shows highly crystalline nature, as you can see it from the selected area diffraction micrographs. And the CZT SSE, as I said, the sulfur to selenium ratio, the percentage wise is 1:1, and it is basically copper poor and zinc rich, which is very important for CZT SSE nanocrystallites. So we have used these photocatalysis experiments for CZT SSE, where we have used with and without converging lens. So as we have seen that without converging lens, the degradation efficiency and the rate constant is slightly less, but with converging lens, there is an improvement in the degradation efficiency, and most importantly, the improvement in the degradation rate constant, for both set of nanocrystallites, either you prepared with topotop or with butylamine octadecene mixture. And as I said, this we have increased, the number of cycles we have increased up to 45, and there is hardly a loss of only 9 to 10% efficiency loss for 45 number of cycles. And even for the different cycle patterns, we have done the XRD, and the XRD pattern doesn't show any change in the crystal structure, no new binary or ternary phases, or no new substance formation takes place, which proves that the leaching of metal ions does not exist here. Only the decrease in the CZTS crystallite size intensity is observed, and which is quite natural because this is because of the overconsumption of the photocatalyst with each cycle, and therefore we will observe the decrease in the crystallinity of these nanocrystallites. And in order to ensure that we have different radical generations taking place, so we have used different scavengers. Typical scavengers we have used is like ethylene diamine tetraacetic acid, disodium salt, EDTNA, and then isopropyl alcohol and silver nitrate. And these different additives, when you add it in your mixture of water and your photocatalyst, it scavenges the electrons, holes, and hydroxyl radicals. So depending upon the degradation efficiency, as you can see from the graph, that when there is no scavenger is added, we get almost close to 100% degradation efficiency. But with the addition of scavengers, be the EDT, 2Na and the AgNO3 and IPA, they capture the electrons, holes, and the hydroxyl radicals selectively. And therefore, we can say that IPA is the most effective radical trapping experiment because the degradation efficiency has reduced a lot. And all the hydroxyl radicals, which are important components for photocatalysis, is being captured by IPA. And we can say that IPA, that is the hydroxyl radicals, followed by electrons and holes, are the main processes which are taking part in the photocatalytic processes. This is the table comparing the degradation time constants with different areas. That is the literature survey along with our present results, and definitely the improvement in the degradation time constant and degradation efficiencies has been done with CZT SSE nanocrystallites. So in conclusion, I can say that multi-component chalcogenide nanocrystals or stoichiometric CZT SSE can be successfully synthesized using hot injection technique and by using different ratios of sulfur and selenium, and particularly the stoichiometric ratio is one of the best, where the sulfur and selenium is 1:1, and where we can get a very effective photocatalyst. And these photocatalysts, we have to render them hydrophilic. We have to change the hydrophobic nature of these ligands. So we have to treat it with L-cysteine so that we get hydrophilic nature of the nanocrystallites, and it can be used for water remediation process. And the electrochemical study shows the least resistance charge transfer, particularly for the stoichiometric CZT SSE. And there is an improvement in the rate constant when we use the converging lens for photocatalysis, and this has been done without using any noble metal additives like gold, silver, or platinum, or even not using even any transition elements. The USP of this work is particularly that the material wastage is negligible. That is, the material requires only 200 microliter per 10 ml of pollutant, that is 20 ml of CZT SSE nanocrystallites to 1 liter of water pollutant. So we can see that how effective it is in taking care of getting the degradation efficiencies. And then the degradation was done up to 45 cycles without any presence of leaching of metal ions. So it has been demonstrated well that CZT SSE is the most promising material synthesized using earth-abundant constituents by non-vacuum process technology, which has the potential to be seriously considered for commercialization for photocatalysis applications. This is the ongoing work where we have used copper, cobalt, iron, manganese, titanium, and nickel. And these are the students, and I was introduced to Professor Ranjana Jha in NSTC in 2018, and I have kept this photograph as a memory. And these are the different students which are working along with me in this area. Thank you very much.
Thank you, Professor Sharma, for a nice talk. So now the session is open for queries. Any question from audience? From online participants?
Okay, I have one question.
Yeah.
Can you go to your conclusion slide?
Conclusion, okay.
So here you are making nanoparticles of chalcogenide materials, right? So there are some other wild semi-metal in this series, in this TMD series, like tungsten ditelluride and tantalum iridium tellurium
Yeah,
4.
but
These
we have
are-
concentrated on typical chalcopyrite, CZTS.
But can you grow some other chalcogenide
Yeah,
materials?
certainly, yeah.
And what is the size of these nanocrystals?
Nanocrystal size is basically, see, it depends on your application. If you want to go for the display application, the size of the nanoparticle has to be smaller. So I have been working because this is one area of my work. And another area is the colloidal quantum dots for display applications, where I use CDSE quantum dots. So CDSE quantum dots by hot injection technique, if you prepare, I get a size of around 2 to 5 nanometer.
2 to 5 nanometers.
Yeah.
So maximum size is what? Larger size.
Yeah, larger size you can, because when display applications, you need to have smaller particle size.
No, I need another application.
How
not
for,
related
yeah,
to
you
this.
can go from, for the larger particle size, you can get even to 1 micron.
1 micron?
Yes.
Oh, that's good.
Yes.
So tungsten ditelluride, is it possible to grow nanoparticles of that material?
Yeah.
It's a wild semi-metal.
Yes, because, in my, maybe, just a minute. इसको slide show कर दो. If you see my profile, which I didn't use, in the here my professional expertise is basically in the all areas of quantum dots. You name any quantum dot and I can prepare by colloidal route.
Okay, that's great. We can collaborate in future.
Fine. Thank you.
Any more questions? Sir, I have one question.
Yeah.
You have shown the Raman spectrum in B mode. So how we can identify that is A mode or B mode in Raman spectrum?
Yeah, typically Raman spectral features are there. So from the literature, you can always match whether it matches with the literature or not. So A mode or B mode, that is definitely defined in the literature, it is there. And moreover, the Raman is very important because you don't get any presence of impurity phases, because in the XRD there is a limitation. XRD always some impure phases matches with your crystalline phase. So Raman is necessary in order to make sure that there are no impurities.
So this also belongs to symmetric and anti-symmetric species, I
Yes,
think.
yes.
So I think there is no more questions. So let us thanks Professor Sharma for giving nice talk.
Thank you. Remove this.
Yes, sir, I'll do that, sir. Thank you so much, sir. request Professor Ranjana Jha to present a certificate of appreciation and a memento to Professor Shailesh Sharma sir.
Now there would be 5 oral presentation, online oral presentation, and first oral presentation is from Ishita. Ishita is here.
Yes, sir.
Okay, please share your presentation, and I would like to request to all oral presenter, please complete your presentation within 8 minutes, 8 plus 2.
All right, sir. I hope my screen is visible to everyone.
Yes, your
Is
screen
my
is visible.
screen? Okay, so good morning, everyone. I, Ishta Gupta, fourth year chemical engineering student from DTU. I'm presenting a small part from our review paper focused on a novel material named as Mexine, discussing its potential in a slew of applications. Coming to the introduction. So, what is Mexine? Mexine is a relatively new class of two-dimensional materials that was discovered in 2011 by researchers at Drexel University in Philadelphia. Mixing materials are composed of transition metal carbides, nitrides, or carbon nitrides, and have a layered structure which is similar to graphene. What sets mixing apart from other 2D materials is a unique combination of metallic conductivity and flexibility, which make them promising for a wide range of applications, including energy storage devices, sensing, catalysis, and water purification. Vaccines are also notable for their tunable surface chemistry, which allows researchers to tailor their properties to specific applications. The chemical general structure formula for mixing is Mn plus 1 uh, XNTX, in which T represents an active functional group such as hydroxyl group and oxygen ion or a fluoride ion, which links to the surface. M represents an early transition metal, and X is either carbon or nitrogen. Coming to the synthesis, so there are mainly two approaches for the synthesis of vaccine, top-down and bottom-up. Top-down synthesis involves the selective etching of max precursors, whereas bottom-up synthesis involves the chemical synthesis of vaccine by reducing metal oxide precursors with carbon or nitrogen sources. So, in top-down method, HF etching protocol is one method which involves selective etching of the A layers of the max phase using hydrochloric acid. Molten salt synthesis in titanium carbide mixing obtained by one-pot synthesis in an air atmosphere. Here, stoichiometric proportions of powdered titanium, graphite, and alumina are combined using fluoride salts, and the mixture is get crushed on a steel die to create a pellet and then covered with a fluoride salt bed. In biofluoride-based etchants, thin coatings of titanium aluminum carbide have been etched using salts of HF like ammonium bifluoride at ambient temperature for a couple of hours, or also titanium aluminum carbide powder has been etched for around 5 days at 60 degrees Celsius or at room temperature. Coming to the bottom-up methods involves the synthesis of mixing using small organic or inorganic molecules. This method has an edge over the top-down method as it facilitates controlled synthesis with adequate size and morphology and surface termination. The bottom-up methods can be applied to prepared mixing using chemical vapor deposition, plasma enhanced pulse laser deposition, and template method. So we worked in conjunction with the University of Houston to prepare the simulations of McSeen to understand its morphology and structure holistically. This is how the structure of McSeen basically appears, and these are the findings on the base of simulation it was performed. Moving on to the application. So McSeen as energy storage devices. Machines have attracted significant attention and they are considered as promising candidate materials for the development of environmental friendly energy storage devices. A large number of studies shows that the vaccines have great potential in energy conversion and storage field, which includes batteries, supercapacitors, hydrogen oxygen evolution reactions, electromagnetic interference absorption, and solar steam generation. Coming to the environmental remediation technologies, chemical adsorbent of dyes which are essential components in textile, paper, and printing industries, despite their practical usage, pose a severe threat to the ecosystem and cause water contamination. The high specific surface area, negatively charged surface, layered structure, high hydrophilicity have recognized mixines as an ideal absorbent materials to the rise for the environmental safety. Mixings in membrane separation of pollutants. Ideal desalination and water treatment membranes should have high flux, high selectivity, stability, and resistance against fouling and chlorine-like chemicals. So here, mixings with a tunable surface chemistry and manageable interior spacing have been proven to be highly practical. Mixings in electrocatalytic sensors. This electrocatalytic platform is an attractive technique for direct or indirect analysis of various environments based on its simplicity, universality, and selectivity. Vaccines have gathered substantial attention from sensors community based on their tunable surface chemistry, hydrophilicity, and active functionalization. Coming to photocatalysis, here vaccines can serve as unique substrates to assemble advanced catalysts to effectively elevate the charge carrier recombination while enhancing the photocatalyst dispersibility and absorption capability. Coming to EMI shielding composites, due to their excellent intrinsic conductivity, vaccines can greatly reduce the consumption to meet the new development trend of electronic components. Till now, vaccines have received extensive attention and applications in the EMI field and become the latest and most popular EMI shielding materials after carbon nanotube and graphene. Combining vaccines with polymer matrix to construct the effective 3D electrically conductive networks can realize the preparation of vaccine EMI shielding composites with low mixing loading, lightweight, outstanding conductivity, excellent EMI shielding performances, and wonderful mechanical properties. Next is gas sensing. Mixines have also been explored for their potential use in gas sensing application. Gas sensing using mixine is based on the interaction between the gas molecules and the surface of the material. In gas sensing, mixines are usually incorporated into a sensing device, such as a field effect transistor, that can detect changes in the electric properties of the material when exposed to gas molecules. This photo shows the schematic illustration of 3D crumpled mixine sphere and 3D crumpled mixine sphere zinc oxide obtained through ultrasonic spray pyrolysis and by using mixine titanium carbide polite at a certain concentration as a precursor. Nitrogen was used as a carrier gas to carry the aerosol into the high temperature tube. After ultrasonic atomization and the moisture volatilized rapidly. The second figure illustrates that the lower Fermi level of mixing causes a slight downward bending of the conduction band of tin oxide. This leads to the extraction of electron holes from the surface of tin oxide, widening the depleted nearby regions in the shallow surface of tin oxide. Coming to biosensing, with the growing human need for new diagnostic methods, easy to use and decentralized biosensors have emerged. Personal biosensor-based diagnostic devices enable patients or healthy individuals to monitor the disease, early diagnose or ensure that a person's health is stable or not. Gaining in-depth insights into the science of materials and the biological behavior of medicine nanosheets and their composites can offer a wide range of promising applications with the potential for clinical translation into human health. In our paper, we have compiled promising research pertaining to biosensors done by various eminent researchers to facilitate further research. Ronsikova and colleagues developed an ultra-sensitive barometric biosensor for the detection for potential prostate cancer marker in urine samples. The biosensor is based on a nanocomposite material consisting of titanium carbide, mixine, and chitosan, which is immobilized with prostate-specific antigen antibodies to selectively detect PSA in urine samples. In this second figure, Raki and her co-workers fabricated a novel enzymatic biosensor for detecting glucose. The enzyme glucose oxidase reduces glucose to glucanolactone and hydrogen peroxidase. Since hydrogen peroxidase generates high oxidation or reduction potential, glucose oxidase is the enzyme which is used for sensing glucose and is immobilized on the mixing glass carbon electrode. The second figure over here shows mixing composites were also used for disease prediction or diagnosis,
Ishita,
especially.
you have 1 minute left.
Yeah, sure, I'm trying to control. This diagnosis, especially cancer treatments. So, in conclusion, mixines have emerged as a new subclass of 2D materials that offer a unique physical and chemical properties, which makes them a promising material for various applications. This paper provides an insight into the current status of mixing in gas and biosensing applications and highlights their potential as a promising material for future research. Thank you so much.
Okay, I think there is no question. So let us thank Ishita for a presentation. Now next presentation is from Hemlata. Let us thank Ishita for a presentation. And now next presentation is from Hemlata.
Ishita, you can stop sharing your screen now.
Hello.
Yes, you're audible and your screen is also
Yeah.
visible.
Okay, ma'am.
Kindly please complete your presentation within 8 minutes.
Yes, sir. Okay, sir. I will try. Good morning, all of you. I am Hemlata. Today I am presenting my research work having the title Development of NO2 Selective Gas Sensor based on Vito 5 microflower. This work is done under the supervision of Professor Mukesh Bhatnagar. Now, sorry. Uh, the outline of the presentation is introduction, motivation, synthesis and characterization technique, result and discussion, acknowledgement and references. Now, first of all, what are the metal oxide semiconductor? The metal oxide semiconductor are the compounds of oxygen and metal such as ZnO, and V2O5, etc. The metal oxide semiconductor are the most versatile group of semiconductor which is influenced by their particle size morphology and doping. There are some advantages of metal oxide semiconductor which are they have easy to adsorption and desorption of gases at the surface, high sensitivity, quick response, environment friendly, and cost effective. Our work is based on V2O5 metal oxide. Now, the V2O5 metal oxide is the inorganic compound which have the yellowish color and with layered structure. Now, why we choose V2O5? because it have the rich layered by layered structure which is easy to intercalate and deintercalate any gases or ion, high electrical conductivity, highly porous, large charge storing capacity, high availability at lower cost than any other transition metal, and it is simply to synthesize as commercial and industrial purpose also. There are some application of V2O5 such as chemical and gas sensor, cathode material for lithium-ion batteries, supercapacitor, and optical switching devices. Now, what are the metal oxide gas sensor? The gas sensor which detect the concentration of various gases by measuring the change in resistance of the metal oxide, such as the carbon and nitrogen oxide, hydrogen, ammonia, and any other gases. The metal oxide are one of the most researched material in the gas sensing application. There are some factors affecting the sensitivity of a gas sensor, such as the operating temperature, gas concentration, and gas flow rate, surface area of active material, chemical composition of material, and morphology. Morphology. Uh, There are some advantage of metal oxide gas sensor. It have the compact in size, low cost, easy to production for commercial as well as industrial purpose, repeatability. There are some disadvantage also metal oxide gas sensor, which is poor selectivity, high working temperature. Now there because we in the recent time there are different kind of gas sensors such as metal oxide gas sensor, thermal conductivity gas sensor, and infrared absorption gas sensor, catalyst combustion gas sensor, and electrochemical gas sensor. In the terms of sensitivity, response time, cost effectiveness, suitability, portability, the metal oxide gas sensor are the best gas sensor, shows the excellent properties. Now, why we choose the NO2? Because NO2 contribute to the problem of air pollution, which play an important role both smoke and acidic rain. It is reported that exposure of NO2 gas to 20 ppm is immediately dangerous to life and health, and the exposure of NO2 above 150 ppm for approximate 30 minutes to an hour result in rapid death. Now there are some possibility to improve the gas sensing property by use of different kind of morphology of metal oxide. The gas sensing property is influenced by their particle size of metal oxide. Now we can improve the gas sensing property by using the novel doping of novel materials such as gold, platinum, Ag, and PD. Now, the motivation of the work is because the most of the work of V2O5 is found on thin film and powder. The hydrothermal method which we used in this research work is very effective for synthesis of pure orthorhombic phase of V2O5 with different morphology. V2O5 also have found an effective sensor for various gases and chemical at different conditions. The literature suggests there are very few reports available on V2O5 as NO2 gas sensing application. Now, in this work, we the synthesis and characterization. We use hydrothermal method for synthesis of V2O5. Structural characterization done by XRD and Raman. Transport properties done by PMS, physical property measurement system, and morphological image we have done by FESAM and TAM, the elemental composition by EDX, and the gas sensing performance by surface current measurement at 1.5 applied voltage by using keyless meter, and the desired concentration of the target gas is obtained by using Ecotech Seren Cal 1000 dilute calibrator. This is the synthesis block diagram of V2O5 microflower where we use ammonium metavalidate and oxalic acid as a starting material and PEG as a solvent. The whole reaction is placed 170 degree in hydrothermal system, and after the hydrothermal synthesis we handle the sample at 350 degrees centigrade for 2 hours to obtain pure orthorhombic phase of V2O5. This is the XRD image of the XRD pattern of the V2O5 microflower. These and ABC are the lattice parameter of V2O5 microflower. By use of Serre formula, we obtain the particle size of the V2O5, crystalline size of the V2O5 microflower, which is 90 nanometer. Here is the Raman peak for the V2O5 microflower, where the 143 centimeter peak is evidence of layered structure of V2O5 microflower. And these are the observed Raman peak and assignment of the band corresponding to the each peak of the V2O5 microflower. These are the FSM image and TAM image of V2O5 microflower, which shows the flower-like geometry of the V2O5 microflower, which are assembled by 2D nanoplate, and the average diameter of the microflower is 4 micrometer. Here is the energy dispersive X-ray spectrum of the V2O5 microflower, which shows the presence of vanadium and oxygen, and the corresponding elemental mapping shows the in red color the presence of vanadium, and in green color presence of oxygen, and the last one shows the combination of vanadium and oxygen. Here is the, because in sensing performance there are porosity is play an important role. This the first plot shows the nitrogen adsorption and desorption isotherm of V2O5 microflower, and which shows by BET calculation we found the surface area of the V2O5 microflower is 9.12 millimeter square per gram, and the plot B shows the pore distribution curve for the V2O5 microflower, which shows the mesopores, which in the range of 0 to 5 there are axis of mesopore. Now the electrical transport characterization done by the physical property measurement system, which shows the single order magnitude increase in resistivity, shows the semiconducting nature of V2O5 microflower, and the plot B shows the activation energy of V2O5 microflower, which is calculated by Arrhenius equation, which is 103 milli electron volt. Now this is a schematic representation of the V2O5 gas sensing characterization of V2O5 microflower, where we use different type of gases to know the selectivity of NO2 selectivity of the V2O5 microflower. This is gas sensing performance of V2O5 microflower, where the gas sensing responds toward 10 ppm NO2 gas with temperature range 50 to 250 degree, having the response 0, 3.0, 10.5, 11.8, and 0 percentage. The highest response at the 200 degree has been used as optimum temperature, and all other sensing measurement done on this temperature. We observe the sharp increment in the resistance when the gas flow is switched on and reached to the saturation by 10-minute gas exposure time. It is not recovered completely when the gas flow was stopped, even at after a long time. This is due to the larger porosity at the surface of the pellet, which keep the molecules trapped and prevent the total desorption process. This is the repeatability curve of the V2O5 microflower for gas sensing, NO2 gas sensing at 10 ppm NO2 at 200 degrees centigrade. And the last plot shows the limit of detection of for NO2 gas for microflower with 0.8% response, which is confirmed. Now here we showed the selectivity of V2O5 microflower against the NO2, where the selectivity of a sensor which depend the measurement conditions such as operating temperature, gas flow rate, gas concentration, and applied surface potential. In this case, we observe the selective behavior of for the other environment gases such as 10 ppm NO, 0.5% S2, 400 ppm NS3, and 10 ppm CO at 200 degrees centigrade. With the corresponding response are minus 2.9, minus 2.3, minus 1.5, and 0% respectively. The negative signs indicate the reducing behavior of the response for V2O5 microflower against the different gases, where S2 and S3CO are well known reducing gases which result decrease in resistance. And the figure we confirm the reducing gas behavior of S2 gas with respect to the oxidization behavior of 10 ppm NO2. Now, conclusion of this presentation is the SAT pattern confirm the polycrystalline nature of V2O5 microflower. The electronic transport measurement shows the semiconducting nature of V2O5 microflower with activation energy 103 millielectron volt. The NO2 gas sensing response recorded as maximum 11.8% at operating temperature 200 degrees centigrade, and we confirm the reducing gas of S2 with response minus 2.9 percentage with respect to the oxidizing behavior of 10 ppm, NO2 with response of 11.8 percentage. Now the acknowledgement section. I acknowledge the Department of Physics, Indian Institute of Technology, Delhi, my supervisor, Professor Mukesh Chand Bhatnagar, Central Research Facility and Nanoscale Research Facility of IIT Delhi, Physical Property Measurement System of IIT Delhi, and Department of Science and Technology for providing the Inspire Fellowship. These are the references. Thank you for your kind attention.
Thank you, Hemlata, for the presentation.
Yes,
Now
thank you,
there is
sir.
a time for one query.
Yes, sir.
Any question from audience? Okay, Hemlata, you have performed your NOT sensing
Yes,
at
sir.
200 degrees centigrade. What happens
Yes.
about room temperature?
So room temperature, there is very small response, means negligible response of the V2O5 microflower, where we can improve this by using the some other novel material or by using the different composite of V2O5, and we can also improve it by the taking different morphology of V2O5.
Any more advantage at lower temperature sensing of NO2?
Yes, sir, it will be beneficial if we can improve it the sensing performance at low temperature. But we can try this by using different parameter for improving the sensing performance at low temperature.
Okay, thank you, Hemlata, for a nice presentation. So
Thank you.
now you can,
Okay.
yeah. Now the next presentation is from Shubda.
Yes, sir.
I think Shubda is here. You can present.
Yes, sir.
Please complete your presentation within 8 minutes. Thank you.
Yes, sir. Good morning, everyone present here. Myself Shubda Kaushik, and I'm from Department of Applied Physics, Delhi Technological University. And my work is on the topic to study the impact of ETL and HTL on the CS2AG, AGGA VR6 based double perovskite solar cells using SCAPES 1D. Starting with the abstract, in perovskites, to get rid of toxicity of lead and to increase its stability, various materials are under research. Among these, we have investigated the efficiency of CS2AgGaBr6 material by varying the optimal HTL in ETL combination. A cell with ZNSC based ETL and CBTS based HTL produce best efficiency of 30.26 at the thickness of 600 nanometer. Coming to introduction, double perovskite solar cell, in addition to their cost efficiency, simple manufacturing, and outstanding efficiency, research also shows that in thermoelectric and optoelectronic and voltaic application of gallium and silver atom-based non-toxic perovskite materials are superior to those which are based on lead and silicon. Double halide perovskites having formula A2MM-X6, where X is the halide, that is iodide, bromide, and chloride, and they have demonstrated a significant improvement in efficiency from 3.8 to 25.5% in last few years. Now, device structure and simulation. SCAPE solar cell capacitance version 3.307 is used for simulation purpose. The SCAPES 1D simulator system uses the continuity and Poisson's equation for electron and hole coupled differential equation to forecast solar cell activity. Device structure. FTO, ETL, CS2AG/HTL/AU. Device structure is used for the simulation. During all the simulation, only parameters of ETL and HTL changes according to the layers used. The parameters of FTO and perovskite layers are same for all simulation. The back contact used in the simulation is AU. AU is a deep warp function metal and inert in nature. This is a device structure we have constructed in our research work, starting with the back contact AU. HTL, optimum HTL is CBTS with thickness 200 nanometer and absorber layer thickness is 600 nanometer, CS2AgGaBr6. And ETL and FTO, fluorine doped tin oxide, is both of 100 nanometer thickness. And this is the band alignment diagram for the same. Simulation using SCAPES 1D. As you can see on the screen, there is a window, it is an image of a window of the SCAPES that appears when we open the SCAPES 1D. SCAPES is a one-dimensional solar cell simulation program. These are the dedicated panels for the basic action. First, run the SCAPES. Second, you can see here the set problem tab. This defines the problem, thus the geometry and the material all properties of your solar cell. Third, you can see this portion indicate the circumstances in which you want to do the simulation and specify the working point. Fourth section indicate what you will calculate, that is which measurement you will simulate. Fifth and sixth is start the calculation and display the simulated curves. As I mentioned earlier, this is the first screen appear when we run the SCAPES program. After the set problem, this is the section which appear on our screen when here we built our device structure, black contact, absorber layer, ETL and HTL. After calculate single shot, this is the processing of SCAPES. And this is the result window which cover all the graph and fill factor, ETA, JSE and voltage. Methodology we opted for the same is, we simulated 6 ETL and 6 HTL as possible combination for double perovskite solar cell. After device fabrication, different environment conditions were set, like temperature is equal to 300 Kelvin. Then we calculated the IV and QE calculation. For each of these cell structure, simulation was performed and the result was recorded and analyzed. Results and discussion. These are the different cell combination we obtained when we varied the ETLs and HTL respectively. And this highlighted one of FTO, ZNSE, CS2, AGGABR6, CBTS, AU. Here ETL is ZNSE and HTL is CBTS. Gives the best result with voltage 1.24, J 29.23, fill factor of 83.38 with the best efficiency of 30.26. Study of different ETL layers. The IV and QE wavelength curves were obtained for 6 different ETL layers, that is IC, ZO, PC, DM, CE, O2, WS2, ZN and Spiro. ZNSE shows highest PCE, which can be because of its high electron mobility, suitable band gap alignment, and reduction in accumulation of charge at ETL layer interface. Study of HTL layers. Similar to ETL layers, we have studied different HTL layers and plotted the same curves for the HTL2. We took the common ETL layer for all the HTL layers, that is ZNSE, and plotted them on the origin software. And it was observed that CBTS and CU2O has shown the 30.26 efficiency, but we took the CBTS because it is commonly used layer and abundantly available, and it has better stability in air. After studying and varying the HTL and ETL, we found our optimized structure with ETL Z and SE, zinc selenite, and HTL CBTS, that is copper barium thiocyanate. And the reason for the same will be that NSE has better photo stability, and it protect and avoid the relatable degradation of absorber layer from the intense UV radiation. And CBTS has tunable band gap, high absorbability, and non-centrosymmetric crystal. I would like to conclude my work in 3 points. We studied effect of different HTL and ETL on efficiency of CS2 AGGA BR6 based double perovskite solar cells. Our study established the work for application of CBTS and ZNSC as future HTL and ETL layers for study and manufacturing of solar cells. Combination of these two layers gives the following cell structure, and which give the efficiency of 30.26 and better other cell parameters at the lower thickness of 600 nanometer. Our study can help the future practical works on the CS2 AGGABR6 as a promising material for solar cell study, research and manufacturing. In absence of any experimental work on material, our study may be considered as a future prediction. These are the references for our presentation. Thank you for your precious time. Have a wonderful day ahead.
Thank you, Shubda, for the presentation. Now there is a time for one question.
Yes, sir.
Any question from audience? Okay, there is no any more questions. So let us thank Shubda for a presentation.
Yes, sir.
Thank you. Now the next presentation is from Rashmi. Rashmi is here.
Good morning, sir.
Yeah, you can present your work. Please try to complete within 8 minutes.
Okay, sir. So I have shared my screen. Is it visible, sir? Is my screen visible?
Yes, it's visible.
Okay. So good morning, everyone. So today I am going to discuss some of my initial studies of the work on the title Study of Pyrazole Derivatives to Act as Electrocatalysts for Energy and Environment Applications. So we have prepared some of the pyrazole derivatives and we have tested them for the first time for the electrocatalytic properties. As there is acute problem of eutrophication increasing in the environment due to increase in industrial water, synthetic nitrogen, urine and urea. So rapid increase in power consumption and various environmental issues compel the scientists to discover new electrocatalysts for detoxification and energy production applications. In the present study, we have used the compost-based microbial fuel cell for waste materials for water detoxification and to generate power. The pyrazoles, which can have various groups like electron donating and acceptor groups, and can act as cathode electrocatalyst, can lead to efficient detoxification of urea and electricity generation. Up to till now, the main applications of pyrazoles are limited to medical field. There are various drugs in which they are in clinical trial and have been used. So to start with, we have done the synthetic studies to make pyrazole. There are many methods for the synthesis of pyrazoles, including chalcones, cyclones, reaction of hydrazines and imidazoles, and Wilsmeyer-Hague reaction of the hydrazones. So in this study, we have used this method, Wilsmeyer-Hague reaction, for the synthesis of 1,3-trisubstituted pyrazoles. The condensation of acetophenones, substituted acetophenones with the hydrazine, they give the hydrazone, double bond N, NH, phenyl, which made to undergo Wilsmer-Haag condensation to give the 4-formyl pyrazoles. So condensation of the estrophenols with phenyl hydrazine gave the respective hydrazone by refluxing in methanol in the presence of acetic acid. The hydrozones are then reacted with the Wilsmer-Haag reagent, dimethyl formamide, and PuCl3 at 0 degrees centigrade, and then heated to 60 to 70 degree for about 6 hours. And then the mixture was poured into saturated solution of base sodium bicarbonate to obtain the 4-formyl derivatives. These formyl derivatives are then treated with acetone in 10% base, that is aqueous NaOH, and the mixture was stirred overnight at room temperature and then poured into ice cold water containing the acid dilute HCl. The precipitates are thus obtained and recrystallized from ethanol to got the pure pyrazole derivatives. The synthesis of these pyrazoles are confirmed by IR NMR C13. We got a characteristic peak of this alpha beta unsaturated carbonyl at the 1643. So I have shown the representative IR of 6A having phenyl groups at both sides. In the 1H NMR, we got a peak due to this methyl at 2.31 and a characteristic peak due to this C5 pyrazole group at 8.25, along with this characteristic peak at in the form of doublet at 6.56 mean value, along with the peaks due to the aromatic region around 7.44 to 7.78. In the C13, we got a characteristic peak of this CH3 at 27. This is the CDCl3 solvent peak in which the C13 was taken. And the peak at 117 due to this group, the CH double bond CH. And the highest peak at 198, this is due to this carbonyl. And this 153 peak is due to C5 hydrogen, C13. So we characterized all the derivatives prepared like this way and then use them for the electrochemical studies. For the electrochemical studies, we use the compost soil, the vermicompost made of cow dung, having the carbon nitrogen ratio of 16. The coin cell used was Cr2032 and the copper electrodes are used for working and for counter. And the reference used by India because it is present in many industrial waste and human waste, 10 molar concentration. The device used is the Palmson's make with the Amstead Forest HR model. So microbial fuel cell was made by this copper layer and then compost, and the cathode portion was made by this copper layering and then putting the pyrazole and then the membrane to separate the pyrazole from the compost. And likewise, we made the fuel cell for the further studies. The activity curve of the vermicompost for this urea, the reference, it shows the maximum at 4.5 hour, and at this time the studies with all the derivatives of pyrazoles were done. So we used all these pyrazoles for making the microbial fuel cell, and the current was studied for the different compounds by taking 10 milligram of the pyrazole, and we showed that one of the derivative, that is 6C, having the fluoro group, which is a very good electron, except these further studies were done with 6C having the fluoro group. The electrocatalytic current studies with the 6C were done at different concentrations, 10 milligram, 20 and 30. And we saw that the current is continuously increasing. And power variation with different concentration of 6C was also measured, and it is showing the trend, the increasing trend. So we can say that these pyrazoles like 6C, which is having the fluoro group, can be used very efficiently for the generation, for the cleaning of the waste and the generation of electricity. So these are the primitive results of the study, and work is still going on by taking the different, some more derivatives having the like fluoro, for which is having good reduction properties, and these are the references. So it can be concluded that the pyrazole derivatives are, these pyrazole derivatives are used for the first time as electron acceptor for detoxification of urea and power generation. Till now, there are many other sources like gold, platinum are being used, but because these are little expensive, so economical alternative is always needed. And the pyrozones can serve as excellent electron corrector at the cathode. And we are making some more pyrozones having electron acceptor groups like chloro. We have done the studies like bromo, and having more than electron acceptor groups for improving the reduction of the microbial fuel cell. So with all this, thank you.
Go.
Thank you very much.
Thank you, Rashmi, for the presentation. Now there is a time for one question. Any question from audience? Okay, I think there is no question. So let us thank Rashmi for a presentation.
Thank you, sir. Thank you very much.
Now the last presentation of the session is from Gaurav Sikri. Gaurav is here.
Mr. Gaurav, are we audible to you? I have sent you message regarding checking your browser settings. Please share your screen if you can. Please reply in the chat box if we are audible to you.
Okay, so I think there is a problem with
हेलो
Gaurav.
हेलो
Yes, Gaurav.
हाँ जी गुड मॉर्निंग सर सर एक्चुअली हम सर मैं आपको मेल कर दूं सर यहाँ से एक्चुअली मेरे ब्राउजर में कोई प्रॉब्लम आ गई है
Okay, no problem. You can present your work later. I think in next section.
ओके सर कौन सा सर टाइम पे
Last. Yeah, you will be informed by the delegate. Okay.
थैंक यू सर थैंक यू सर
So I think I would like to conclude this session.
Thank you all the participants, and let us give a big round of applause to everyone, online and offline participants. And I think we should also give a round of applause to Professor Dheeraj Kumar Singh for chairing the session. And I would now like to request Professor Ranjana Jha to present a certificate of appreciation to sir. Thank you, ma'am. Thank you, sir. So now we can, I think, pause for 10 minutes for a break, and then we will start session 2 after the high tea break. Thank you, everyone. Ma'am, 10 minutes. हाँ. We will reconnect after 10 minutes.
Recording stopped.
My browser is not joining audio. एक बार मैं उनसे बात कर लेता हूँ, उनका फ़ोन आया था क्या आपके पास? हाँ हाँ, मैं पूछूँ उनसे, मुझे बात करने के बाद।
our second session. So for that, I invite Professor Anjana Sarkar, Professor and Head of the Department of Chemistry at NSUT, to chair the session. Let me give a brief background about ma'am. Her areas of interest include organic, bioorganic, and bioinorganic research. She has published more than 50 publications and was also a PI in an AICTE-sponsored project. So with this, I would like to invite ma'am to kindly chair the session.
Recording in progress.
Good morning. I invite Professor Arthur Hussain to give his invited talk on the topic is Sustainable Approaches in Management of Solid Waste, a Step Towards Circular Economy. Now, a brief about Professor Arthur Hussain. He is a professor and head of Civil Engineering Department, West Campus, NSUT. And his research interest areas are industrial wastewater treatment, water quality management, solid waste management. He has supervised 6 PhD students and 6 are still pursuing, and has more than 170 publications, then 65 MTech dissertations. He has published many books and serves as a reviewer for many reputed journals. He has 18 ongoing consulting projects. Professor Arthur.
So thank you, Professor Anjana Sarkar ma'am, for such a nice introduction. Thanks a lot. So, good morning, all the distinguished guests and eminent speakers, delegates, all the participants, students, my fellow colleagues, and all the organizers of this conference. So today I am here to interact with you on a very burning topic, which is, I think, nowadays a need of the day, and a lot of research is still going on. But there are many things that we are not aware about it, and we should discuss about it, and we should have an idea about it, so that further there are many young researchers here who can take into considerations on such issues and aspects and go on further research on the topics. So the topic is sustainable approaches in management of the solid waste, and it is a step towards the circular economy, because previously we were not aware about all such aspects, simply that we are the consumers. On the consumer side, we are utilizing a lot of things, and we are just, after using it, we are discarding it as a waste. And ultimately, it is polluting or harming the environment, or it is a burden on the environment, we can say. So the thing is, for the circular economy point of view, that is a state economy, but for the circular economy, we should rethink about it, that how we can use our best, or what we can do, what we can utilize the best out of this waste. So it is reuse, recycle, or best management practices which can be utilized for, we can say, zero pollution, or we can say zero wastage. So let us have an introduction about the waste. It is organic or inorganic waste materials that we see in our daily life, such as furniture, clothing, bottles, we can say clippings, empty cans, batteries, etc., etc. Solid waste thus encompass a heterogeneous material. It is organic, it is inorganic, and it is inert material or mineral waste. And what we think is that the waste is having a very little value, or it has no value sometimes. So we are disposing it. But it is a resource, and we can classify based on the emergence from our homes, residential areas, industrial areas, commercial areas. So it is garbage, ashes and residue. We have construction and demolition waste. Hazardous waste is a different category. that some waste are having certain properties of corrosivity, reactivity, and other aspects. So these particular properties makes them hazardous waste, or it is toxic. Then street waste, the garbage, or from the parks, plots, paper, cardboard, leaves, branches of the trees, and so. And bulky waste, large household appliances are there, refrigerator, washing machines. We can say related to the electronic waste also. So this is the schematic representation of a diagram of the solid waste. That is, it can be categorized as municipal solid waste, agriculture waste, industrial waste, and it can be categorized as general waste or hazardous waste, and non-hazardous waste and hazardous waste. So here we are dealing with the problem, and my main focus is on the municipal solid waste, which can be utilized because all around, particularly mainly in our metropolitan, even in the metropolitan cities, we are not able to cater it properly. We are not able to manage it properly. And we can see a number of places, big heaps of these waste lying around. And what will happen in the next few years, that we are not able to have enough land also, because in land cost requirement, all such aspects and economy aspects are there. So this is the situation that we are dealing with. So generation of these waste includes the commercial, we can say household, construction, and horticulture, institutional. All this makes the municipal solid waste. And there is simple some data that is related to the current scenario, that urban waste is generated in India, in metric tons, and lakhs of the tons is waste. And it is estimated that construction industry even alone produce 25% of this, and rupees 1600 crore requires for the treatment and disposal, yes, daily. And the industry is also discharge about 150 million tons of high volume hazardous waste every year, which is mostly dumped in the open low lying without unengineered landfill sites, we can say, or where they are, we can say, remain unexposed, we can say. Then the important thing here is the per capita waste generation. That is an important aspect for the, we can say, quantification of the waste, for its collection, transportation, and other aspects are there. So it is lying from a small city to the, we can say, metropolitan city. It can vary from 0.2 to 0.6 kg per person per day. So these are the some waste collection efficiencies in bigger size cities, 70 to 90%, and even in small towns it is there, but 50 to 60%. And there is a very less budget that the local authorities or organizations that are investing on it, only 5% of their budget. Solid waste is transported inadequately. You have seen in many places openly, or it may be lying in so many places in the streets, on the roadside also. And the collection process is not so good, not so healthy. Out of the total waste generated in India, more than 50% of the waste is organic. This is the, actually from the management point of sight, that what we can do, how we can deal with this waste. So you can see the municipal solid waste tons per day and per capita. So even you can see the cities like Ahmedabad is there, like Chennai is there, and then we have Lucknow is there. So they are, you can see per capita waste generation is too high. And many places at the lower side, you can see, Nagpur is good enough that it is around 0.273 per person per day, per capita per person, in terms of the kg, I can say. Or there are other cities also, like Mumbai also, Delhi also. So you can see there is a lot of variation. So that is because of the healthier practices, good practices, or they are actually adhere to the rules, regulations, and acts, then only it can be possible. Major deficiencies we have, we can see littering of the garbage. Many places you have seen provision and operation of the interim storages. Then we have irregular garbage liftings, transportation systems, processing, treatment, final disposal, and we can say its effects on health, socio-economic conditions. So we are wasting a lot of money on this, on the socio-economic health aspects, because of these problems of these waste that is arising around us. Many times we have heard about the Delhi itself, a lot of that is, we can say many times these our landfill site, they catches fire, and lot of pollution is there. So that also creates problem. Many times we have seen that road is being constructed, and because of the gaseous part that is moving through the ground that actually breaks those roads. And every time this problem is happening near the landfill sites. And even groundwater is contamination, lot of groundwater is contamination because lot of the liquid is being generated. And you can see a number of places you will find these things, or these, we can say, a number of places you can find how in a haphazard manner this waste is lying. So general composition from the management side, what we can say is that 40% of the food and garden waste, 5% of the glass, generally comprising, in Indian context I'm talking about, and in generation rate is 0.3 to 0.6 kg per capita per day. For the commercial it is little bit lesser. For street sweeping, yes, 0.05 to 0.2, institutional 0.05, and industrial 0.1 to 1. So these are the waste composition that we generally categorize. So when we are taking a waste, or when we are seeing a waste that is lying, or we want to characterize it, so first of all is the physical composition of that waste. We should be aware about it, that how much of the wet waste is there or food waste is there, how much of the paper, cardboard, plastics or individual components of this waste is there. Then only we can decide further what we need to do. So characteristics also depends on the income of the people, or we can say the around area of the people where people are using it or throwing it or discarding it. So that is based on low income and high income groups. So you can see the individual component of this waste varies with respect to the group of the people, high income group or low income group. Then we have a waste disposal methods. Generally we follow land dumping, 89 to 90%. Composting a little bit, very less, it is 8.6%. And others are very, very less, that is 1.6%. So around 90% of the collected waste by civic authorities of India is dumped into low-lying, unengineered, we can say, landfill sites, which are not properly designed. So properties of the solid waste we need to determine before we are going to management site. That is the physical composition or physical properties include identification of the individual components, analysis of the particle size, moisture content and its density. Then chemical properties, we should have approximate analysis, ultimate analysis, and fusing point of the ash and its heating value in terms of the energy side. So this physical includes specific moisture content, particle size and all that. Chemical also I have discussed. And the biological, it is important in considering the organic part or organic fraction. When we are going on the biological processes such as composting, anaerobic digestion, or we can say waste to energy options. So typically specific weight, why it is required? Because it is required when we are going on the transportation side. When we are going on the transportation or collection of that waste is done, so we need to assess that how much of the vehicle are required, what should be the volume of per vehicle. So we should know the density of that waste, because on basis of the density on the mass which is coming out, we can calculate the volume. So volume is very important part of the waste which is coming out. So for the volume, we require densities of all types of the waste. So this is basically, we can say, for the trucks that is taking place, or when we are compacting it on the landfill site. So we can assess the volume of the landfill site for the next 10 years, 20 years and so, based on the density of this waste. And typical proximate analysis is also required for its properties, that is moisture content, because many of the processes that we are using, whether we are going for energy process or we are going for other processes, moisture content is very important. Volatile part is also very important when we are talking about the organic matter. And carbon part, yes, fixed carbon is there, and we can say organic carbon is there, TOC is there. Then ash content, how much it will be remaining after overall in a combustion process, incineration process, or other processes that we are using. Chemical composition of typical waste, we have some nitrogen, metals, ceramics, hydrogen, but major part is moisture content in terms of the water, we can say. Carbon in terms of the, we can say TOC, or I can say total organic carbon, or that takes part in any biodegradation process. Oxygen is also there, so these are required. Then fusing point of ash, that is required when we are going to incinerate the waste, because this is incinerated in generally 2 steps. First step is the removal of the moisture content of it. In the second step, we are burning it completely. So that is the fusing point of this ash, we can say, and typical range of this is 1100 to 1200 degrees Celsius in an incinerator. But incinerator burning of this waste has lot of problems of the fumes, exhaust gases, we can say, or the sometimes to retain those gases or to recover those gases through the water or scrubbing systems, that again produces a lot of wastewater. So we have a number of problems that exist in the incinerator also if it is not properly operated or maintenance is not done properly. So it will again create a lot of pollution. Then we should decide through the chemical formula, we can calculate the calorific value of that waste. And for that we require the CHNS analyzer, where we can calculate the carbon, hydrogen, oxygen and this particular ash content for different types of the, we can say through the characteristics, or we can say mixed waste or an individual waste I am talking about. So we can calculate its chemical properties, and for that we can use the Dulong's modified Dulong's formula, where in terms of the kilojoule per kg we can calculate the carbon part, how much it is having, the hydrogen part and oxygen and the sulfur part is there, and through that we can decide that this is the calorific value of this particular waste. So my option towards management side is whether I should go for incineration or I should go for some anaerobic biological process where I could recover the biogas from this waste. So that all depends on this energy content, because there is a difference in the Indian conditions and the conditions that are abroad, like in US, UK or other countries. The calorific value is an important part. Our plastic and their plastic is very much different. And the calorific value of the plastic in India or such waste that could be burned is low calorific value. So whatever we are implementing, we are not getting that much of the energy. So sometimes the system can lead towards failure, because the energy that we are giving, we are not producing, or we can't produce that much of energy. So sometimes we should be careful about it, that the calorific value is an important part of it. Then we have biological properties. So we should have volatile solids content, we should be aware about it. And very important part in the biological process, particularly in the anaerobic digestion, the end products are quite stable, but gases produced are odorous, and that could create problem because they could be corrosive also, they could be odorous. Many places around the plant area, the people are suffering, the instruments are suffering, their whatever the daily usages, say I'm talking about the refrigerators or the daily utilities, they are suffering because of the hydrogen sulfide gas H, that is H2S, the end product of the anaerobic process, other than carbon dioxide and methane. So appropriate transformation process is required. That means we should go for separation, reduction, combustion, and moisture content is very important part, because it could lead to the change in the pH conditions during the biological process, and it can hamper the biodegradation process directly also. So moisture content is an important part. Then CN ratio, because every microorganism is having the cells, and cell is having requirement of the cell is carbon, nitrogen, phosphorus. This is the major nutrient. So CN ratio is very important. Higher and lower CN ratio can cause hamper the biodegradation process. So then design and recovery methods, we can say, where we can reuse or recycle or conversion products plus whatever the energy is required, or we can say we can get. So solid waste management includes the collection, sorting, recycling, segregation, then useful product formation and marketing use. This is the entire management system that includes the waste generation, then its storage, collection, transport and transfer of the waste, processing and recovery at the management site, and disposal, which is the least option. So treatment and disposal of the solid waste, that includes reuse and recycling, then composting, incineration, pyrolysis, landfill. So landfill is the least option, but the most preferred option is either it should not come into being, that is the least generation. Then if it is there, then reuse, recycling, composting, then incineration or pyrolysis, where we can produce biochar also. So biochar has so many applications in the agricultural field, in the adsorption process we can use it. So there are so many processes where we can utilize this from the waste. So this is the hierarchy of this particular any type of the waste we can say. So least option is that is unmanaged waste or landfilling waste is there, and the highest is that we should avoid that it should not come into the atmosphere, and we should have certain waste minimization techniques we can use, recycling, reuse, waste to energy options. We have incineration, or either we can go on the biological process, anaerobic degradation. Then we can go for physico-chemical treatment also if it is not possible. So these are the general stream of the solid waste activities. We have different types of the waste and where we can utilize these. At the end of it is the leachate plant. You can see that even at the landfill site there is a problem. If we are using engineered landfill site, then again the leachate will come out. You have to treat that leachate and you have to dispose that. So that ends up there. So we have biological treatment methods, composting, biogasification, material recycling we can do, and we can go for the thermal treatment like the incineration process, fuel burn, mass burn, we can say biomass burning. Then landfill gas use we can go for the usage because it is left unattended most of the landfill site. So we have different environmental sound technologies that we can use. So first of all is the quantity and characteristics of the waste we should know. Then we should be aware about the change in the climate and seasonal variations, because this is very important aspect. Sometimes moisture content is too high, sometimes the moisture content is very less. So that changes the physico-chemical characteristics of that waste. Particularly in urban area and in the rural areas it is different. Financial constraints are there, so many cultural constraints are there where we cannot avoid, and management of the, we can say, technical resources. So this is a simple example that how long a waste can be decomposed. You can see from a train ticket up to a plastic bottle, it took from 2 weeks to 100 years for the different wastes to decompose, to get eradicated from the environment. So we have to think about it so that this plastic bottle could be degraded within 2 weeks only. So we should have such technologies. So there is a new concept. Basically, previously we were following the straight, we can say, economy, but nowadays we should come, or we have adopted, or we should adopt the circular economy, where we can say that anything which is coming to the system and we are utilizing it, it should not go to the environment, it should not harm the environment, and it should be at its minimum. So circular economy includes raw materials, its design, then production, manufacturing, distribution, then the consumer side that we are using. Then after being discarded, it should go to the collection site from where it should be recycled, reused, or it should go to the other options. So recycling, we can go for a number of things that in our house also, or around our house, we have many kinds of glass, paper, metal, plastic. And very simple example is that in India, these kabadiwalas are the most, we can say, very unorganized sector which is organizing this waste at a very technical level and making it possible. Then recycle and recovery of the materials in the municipal solid waste, we can see that around this 12% is recyclables, then 47% is biodegradable, and 35% inert material, while 6% is the others, we can say. So we have different options for this. We can use and we can recycle, reuse, or we can transform from one, say if this particular material, I can make it some other material which can be reused, or which can be recycled to some other form. So this is a simple example that by recycling almost 8 million tons of the metals, aluminum, steel, and mixed metals, we are eliminating greenhouse gas emissions of around 26 million metric tons of carbon dioxide equivalents. This equivalent to remove more than 5 million cars from the road for 1 year, you can see. So this is a simple example how we can say compare. Plastic management, because in India it is having low calorific value as compared to other countries, and we have started plants in Delhi and other states also, but still results are not good, or we can say results are not, we can say, within our what we were assessing or what we want, or these are not satisfactory. There are many plants, I think 2 or 3 plants in Delhi, and few are likely to be started. But because of these are beyond our, we can say, not our expectations because of the low calorific value. In road construction, we have done it. Yes, we up to certain extent, we got some success in that the plastic bags, waste were separated, and it was used in the bitumen, and it was spread on the road, and the mixture is transferred on the road for laying, and it is that we got the better results or good satisfactory results. Then we have cement kilns also, where we can go for the recycling of the plastic, but material having calorific value of at least minimum 2500 kilocalories are accepted as alternative fuel. Otherwise, it is not. Or we can go for the biochar, that for the pyrolysis process. And these are the simple techniques that we generally apply, because most of the virgin plastics, or the plastics is having around 6 or 7 layers that we use. And these plastics can be separated out by the simple solutions. The recycling rate of this particular solution, that is DMCHA, is around 99% or greater than this. And we can get from these particular, we can say, plastics, we can get EVA films, PET films, pea powder of a higher quality than the traditional recycling methods. The solvent can also be recycled. Again, the question comes, what should be done to the solvent? It is again a pollutant, so that can also be recycled. So this is a very good and a simpler method that we can carry out in the lab also. Then we have bio-based plastics nowadays, that is the PHA, we can say. Polyhydroxy alkonates are there that are synthesized completely by many types of the microorganisms or bacteria. So within, okay, 2 minutes, 2 minutes, okay. So let me come some of my studies that I have done. I will share with you, okay. So we have prepared garbage enzyme in our laboratory, and this garbage enzyme is simply prepared from the vegetables that are being discarded, peels of the vegetables or fruits that are discarded in our home. We can prepare at our home this garbage enzyme, and very simple method is you can use jaggery and 3 ratio of the organic waste that you want to make it, and you can ferment for 3 months. And after 3 months, you can filter the residue, clear, you will find this liquid, and this liquid is having so many benefits. You can go for the floor cleaner, toilet cleaner, kitchen cleaner, dishwashing, it is air purifier, clothes detergents, waste treatment, body wash and hair care, insect repellent, pesticide, and it is for the fertilizer also, we can utilize it. Then we have done an experiment for the maggot larva. You might have seen big fly, that is, one is the small fly at our home, that bigger fly, that is very dangerous, actually that is called as that, it is very dangerous. So that larva of that fly can be utilized for the accelerative or acceleration in the biodegradation process. We can accelerate the biodegradation process, and this takes around 5 to 8 days to produce this larva, and this is the best, we can say, that makes the biodegradation process very accelerative. And we have publication on these particular enzymes and larvae, but nowadays we are trying for the black soldier fly that is basically found in US. So we are trying to produce it here so that we can have more fast accelerative process, because that could, the main problem with the solid waste or many of the solid waste is the lignin and cellulose. So lignocellulose part can be degraded by this particular black soldier fly. So thank you very much, and this is all about, I can't continue because of the lack of time, because many things I was thinking that I would share, but thank you very much for.
Thank you so much, sir. Let us have a big round of applause. We have time for one or two questions, if you guys have any questions. Even the online audience can ask questions. So now I request Anjana ma'am to present a certificate of appreciation and the memento to Professor Athar Hussain.
Next is so next I invite Dr. S. Nileshwar, IP University, for an invited talk. His topic is challenges and limitation of synthesis of thermoelectric materials. Now a brief introduction of Dr. Nileshwar. He's assistant professor in the Department of Physics in IP University. His area of specialization is nanomaterials, thermoelectric materials, superconductivity, magnetic materials. He has more than 25 publications. Thank you. Please. And try to make it short.
Yeah.
As we are running.
Sure.
इनको तो लगाना पड़ेगा. Sir, actually you might need to because we are also streaming it online for the online participants. So sir, I think you would have to transfer your PPT to us. Because this is hybrid mode.
Maybe can you give me the okay, and can I open my
email?
Because you should tell that. Otherwise I cannot put video.
Okay, sir.
Okay, can you do okay, leave it. No, I don't know how.
So can you connect to Zoom?
Yeah,
then,
sure.
Then you can share your screen.
Maybe I don't know whether internet है आपके पास इधर.
Yes, sir.
Can someone Zoom? I don't know whether I have the Zoom here or not.
So I think, sir, it's okay. We can continue this way, and I'll just ask them to share your.
Just you intimate, then I can bring the.
Okay, sir. Because we intimated yes through email. हाँ सर के उस पे कनेक्ट कर दो.
Maybe Zoom कैसा करना है इसका?
Sir, for Zoom, do you have Zoom, sir?
Maybe I can install.
Yes, sir. Zoom is there, sir.
मीटिंग आईडी बताना.
So meeting ID is 874
874
7933
7933
0889
0889.
Yes, sir.
Join. Right.
Yes, sir. इतने सर को कनेक्ट कर दो उधर.
Maybe I did not check.
नहीं सर, that's fine. That's fine, sir.
आपका इंटरनेट हो गया, कनेक्ट हो गया ना?
सर इंटरनेट कनेक्ट कर दो इस पे पहले, तभी तो नहीं. वाईफाई का पासवर्ड क्या?
मैसेज ठीक?
Yes, sir.
हाँ? 874
7933
7933
088
088
9.
9. Thank you.
Passcode is 15089.
15089. 15089.
Let me ask. हेलो सर, एक बार जल्दी आ जाइए, यहाँ पे प्रॉब्लम आ रही है।
नहीं आ रहा है।
सर का वो लैपटॉप कनेक्ट करना है, लेकिन मीटिंग पासकोड गलत है।
150897
897. Okay. Just 150.
गलत प्रिंट हुआ है 150897 7
कितने इस करंट
लगा ना
मन निकाल दिया है वो उसका।
अब बताइए
मेरे को लगा सुबह
फिर
सर कनेक्ट नहीं हो रहा है लैपटॉप को।
उस वहाँ से
लेने रहे हैं तो
ये तो प्रॉब्लम आएगी। HDMI दोबारा ट्राई कीजिए।
ऐसे कि एक्चुअली वीडियोस भी हैं इसमें PPT।
वो कल भी परसों एक बार हुआ था ना, तो वो नहीं हो पा रहा है, कनेक्ट करना मुश्किल होता है।
पेन ड्राइव है,
पेन ड्राइव तो है,
कॉपी कर लेते हैं पेन ड्राइव से।
नहीं तो ईमेल ओपन कर देंगे। चलो
हाँ सर, कोई नहीं।
हो गया।
नहीं कनेक्ट नहीं हो रहा तो
सर विल कलेक्ट द PPT in a pen drive.
That's what I asked you. Do you have any
But sir,
new?
I did not have the pen drive.
I will format it. No information is there, na?
there are information but not sensitive, it's okay.
Format कर सकते
फॉर्मेट नहीं कर सकते सर।
वो because this is some important data है। कोई वायरस है तो this is a conference where क्या हो गया?
You can email it to the
Yeah.
ICAMET email ID because I have it open.
Oh
over
yeah,
here.
just one second. I will, and after that kindly delete me. Delete that one.
Sure, sir.
ब्लिंकिट के साथ जुड़ें और पाएं 1 महीने में 50,000 रुपये तक कमाने का मौका। साथ ही पाएं सिंगल स्टोर पिकअप, शॉर्ट डिस्टेंस ऑर्डर्स और 10 लाख तक का इंश्योरेंस। तो जुड़ने के लिए अभी दिए गए इस नंबर पे कॉल करें या फिर नीचे दिए गए लिंक पर क्लिक करें।
जन गण मन अधिनायक जय हे भारत भाग्य।
इसमें हाँ
सर फॉर्मेट कर दीजिए,
कुछ फाइल नहीं दिखा रहा है।
जनगण
Good afternoon, everyone. Sorry for the technical delay. And first of all, I need to thank for the organizer, International Conference on Advanced Materials for Emerging Technology. And today I'm going to talk about what are the challenges and limitation of synthesis of thermoelectric materials. Before going thermoelectric materials, just I want to give small, you have the energy. The energy have very big impact on our day-to-day life. How energy is important, just I will go very, look at our India energy role. We are not, even though we say we are 1.3 billion people, but the energy consumption, still we are not in the top position. So unless until you use that energy perfectly, you cannot lead the world. Whatever the technology we need to develop, we need to utilize the technologies more perfectly. If you look at United States, China, Germany, India stands and forth for your utilization. And when you look at just I'm going to consumption of overall energy, and here most of the energy is going to be waste. And like a heat and another forms, distribution forms, how one can utilize that energy perfectly, that is one of the challenge. And using that the waste heat into perfect manner, and it is one of the challenges for the scientists to develop the new materials which can use. Suppose you are driving a vehicle which is a diesel or petrol, you use only 33% of your petrol to run that vehicle. Rest of this energy is going to the waste. So how to increase the efficiency of that material, that all depends on how you can develop your smart materials. And these waste materials, when you talk the energy, it is one is the renewable, non-renewable, and all we are know there are n number of non-renewable energies. I'm not going to talk much about here due to the time limitation. Just I am going to stress one of the recent studies, and if you look at other renewable energies, entire globe using only 2%. And 2020. And in 2025, it is expected to be used only 3%. In 2035, it is going to be 4% of total renewable energy. Means the day by day, if you look at very carefully, the natural gas system is increasing, and it means the global warming is going to, and still we need to, the oil, depends on fossil fuel oil. Every year it is going to be systematically decrease because the resources are going to dry after some time. That is the one thing we need to think and how we can do it. And some of the prospects, and here when you look at when you look at waste heat, where you get the waste heat? Everywhere, from thermal power plant to nuclear power plant, automobile, and in a day-to-day home appliance, and everywhere you will get. And this waste heat, can I trap? 66% of waste heat is going to be wasted. And is there any ways to trap that waste heat? That is one of the challenges for our young scientists, our coming budding scientists, and need to be looked into that. And in that, as I discussed, when you want to develop this waste heat trap, you have the from temperature range from 0 to 1500 Kelvin, means below room temperature, above room temperature, and there are material, standardized material, bismuth antimony will work at low temperature, bismuth telluride room temperature, lead telluride middle temperature, silicon germanium very high temperature, it is around 1200 degree Kelvin. And these are the some are micro optoelectronics, some are waste heat recovery system, some are automobiles, some oil and high-end industries. And okay, we are going to develop this waste heat into trap into the use, and what are the reliability and what is the advantages of this thermoelectric. And reliable is, it is the maintenance free, low maintenance, no complexity, fix it and forget it. And it will not depend any orientation, anything. And second question will come, is it environment friendly or not? Definitely it is a environment friendly and vibration free, no noise, no carbon monoxide emission. And definitely it will, the efficiency, boosters efficiency and lifetime also. And we will also take the primary use of this. When you use the thermoelectric material, you use as a temperature stabilizer, and for wherever you get the temperature difference more than 30 degrees, you can use as a IR detector, and some other heating pump, power generation, as well as cooling the system. If you are overusing your laptop, it will be heated. For example, in Delhi, everyone will experience the cooler air condition fails after 45 degrees. Then the people are mounting on that thermoelectric material coolers to cool it, and so that the efficiency of the cooling efficiency increases. And here there are different aerospace, automotive, commercial, IoT, all this medical, it is already using from nanovolt to few high-end volts that rockets may be used. And now, what is the basic principle? As everyone knows, is a Peltier effect and Seebeck coefficient. And Peltier effect is conversion of electric energy into cooling. Conversion of waste heat into electrical energy is the Seebeck coefficient. One is the power generation, another one is the cooling. Very simple. The principle is very simple, and it is very easy to, wherever the delta T, when you go outside and you will get the temperature difference. Human body, inside temperature is different, outside temperature is different. The people are now using the thermoelectric shirts for especially the people keep warm or cool. And this is here the basic. You have the two components, N and P type, and N type hot side and cold side, you can, where the temperature difference is generated, and you need to be, just you see how if one circuit N is there, another one is for the cooling side, it will go to the P side, and then this is the NP circuit will go, and these model, single uni model, coupled together, and the global thermoelectric predicts from 2027 at least this efficiency. Recently the efficiency of the thermoelectric model, you can see the top side, top right, it is a view of PN junction. Real one is the left side bottom one, And on the top left, this is the thermoelectric energy harvesting other. It is a zero emission. The beauty of this is zero emission, and by 2040 in your day-to-day life, you use most of the thermoelectric material, like everything for cooling and many even for your, one of our collaborator, my mentor, working on that to heal your pains. You are getting the headache and the temperature your body heated, just to put the thermoelectric material and make it point cooling system is going to be developed. And these are the things are working, and this is a very big market, big area of working. And already in 2012, and Denmark, they developed the BMW and they use the thermoelectric model. The efficiency increases 32%. Just they trapped. And here, okay, one beauty. What is the how the thermoelectric? This is entirely depends on the figure of merit. That is a JT. That is a one is a Seebeck coefficient, electrical conductivity and thermal conductivity. Okay, very simple. Everybody in the lab we can do and measure it, and which is more accurately you need to measure. And Seebeck coefficient, if you want, you need to choose the best material. How to increase the Seebeck coefficient? And beauty of the nature is, if you want to increase the Seebeck coefficient, simultaneously electrical conductivity will decrease. And if you want the electrical conductivity increase, the thermal conductivity, Seebeck coefficient and thermal conductivity. Thermal conductivity, but you need to make the best figure of merit to optimize this. Seebeck coefficient should be high, electrical conductivity should be high, as well as thermal conductivity. As a material scientist, you need to make the engineering this material and do this. And here, when you develop any material, it should be for the people, for the earth, and it should be used for the future. And it also should be very good eco-friendly. Okay, very good, materials are very good. How I can select the material? And this is one challenge. You have a insulator, semiconductors, semi-metals, and metals. How to choose? With the carrier concentration and the best thermoelectric material in the and this is the large, these are the unusual band structure, electron crystal structure, quantum confinement. These are the best ways. And I am happy to inform that these are the materials we are able to develop in our laboratory at IP University. And bismuth telluride, bismuth selenide, lead telluride, lead selenide, and tin-based thermoelectric material, silver-based. And what we are doing here? We are doing the quantum zero defects, creating anisotropy, and two-dimensional, inserting two-dimensional, one-dimensional system, and quasi-nano inclusion. And this is the basic structure of bismuth telluride, lead telluride, CJTS, copper selenide, Saturn selenide, silver antimony, SNTE, calcium telluride, magnesium. And these are the state of art of the figure of merit of thermoelectric material. And you can see some of the thermoelectric material are reached the figure of merit around 3. And we are using to fabricate very simple high energy ball milling, as well as furnaces, and melting technique, and microwave method, and rocking furnace, and ball milling, melting. And just this is the simple SNSE. Just we'll take the SNSE and as per aspect ratio and do the thing. And now in the high energy ball milling, you need to mix, and you can see the ball mill ratio, final product here. And the parameter here is to make this, you will have the milling time, ball to ratio, on-off cycle, milling ball dimensions. One need to be optimized. For that, it will take time. And for simple one example, and one of the complicated system, I want to show here, MN4 SI7 it have the 6 or 7 phases in a single system. In 6 or 7 phases, we are able to make the very high pure synthesis using the high energy ball mill system. And you can see the standards data MN4 Si7 with the M1, M2, M3, M7, and you have the usually you will get MNSI, MNSI and MNI Si2, and there are 6 phases, but MN4 Si7 we are able to get at this last M7, M8, M9. And to make the simple pure phase, you need to play little more. And similarly, we are able to do the simple SNSE system also. It takes and high purity. And now, melting tank, just you take the melt and do the annealing and simple growth. And this is a rocking furnace to make most of the time we get the reproducibility and the density problem will vary 3 to 4%. That will give the very huge difference in the thermoelectric properties. In that case, just we need to make this rocking furnace is in our lab we designed this and to make the more perfect uniform in the sample, and we are able to get the 100% reproducible, and the cost of this is not much, and we can go up to.
Request you to wind up soon.
Sure.
Within 5 minutes because DC service coming, then we will.
Yeah. Okay, just finally I will wind up within 3-4 minutes, and this is the ultra low thermal conductivity high figure of merit in SNSE single crystal in 2016. It is published by Zhu et al. In Nature. Then we are fascinated to know that figure of merit SNSE is going to be the future. Then we tried in our lab to make the 4-zone furnace, and we are able to develop this single crystal, and then this is a XRD and Rietveld analysis, perfect fitting and high perfect density. Then unfortunately we did not get what they reported 2.6 because their density is 88%. And here you can see the heat capacity at 800. They have the very anisotropy. This anisotropy gives very big change. And now you can see we did the intrinsic thermoelectric single compare, and we are able to calculate our power factor, and exactly we batches with the literature and our sample, and somehow the thermal conductivity Zhu et al. Reports very low, and we got very high thermal conductivity. And then we figure of merit we did for geo and single crystal. Our crystal have the very low figure of merit due to the highest thermal conductivity. Then we did all density measurement, other things, and finally we are able to get the measurement thermal conductivity SNSE low temperature to high temperature by the father of the thermoelectric street, and in his lab we went and do that measurement, and this measurement we did like with the access also, and we got the very good results. And finally the density of we challenged the Nature paper, and we also able to publish the intrinsic in Nature in 2016. It is also accepted in Nature by challenging one of the biggest group, and this really motivates us to do and you can now, because many of the students you will think where you are in your pacemaker thermoelectric materials, you are not giving any external supply. In pacemaker thermoelectric already using successfully once you install 10 years life. And and I need to thank my collaborators, Professor Aparao, and Professor Wu, Professor Vaivai Chen, and one of our theoretician, Anjana Bagga, and my research scholars. And MKO is Y123 inventors, high temperature super. And
Thank you, Professor, for your nice talk.
Thank you very much, sir, for your nice presentation. Now I request ma'am to please give the certificate of appreciation to sir. सर ये साइड आउट करना है
दुष्यंत जी
इसको
स्टॉप प्लीज।
अच्छा ठीक है मैं ये बंद ही करना है वैसे भी।
बैनर लगा दो पीछे।
ठीक।
Recording in progress. Recording stopped.
A very good afternoon to all the dignitaries, chief guests, invited speakers, guests, delegates, participants, and all the members of NSUT. I, Dr. Nancy Gupta, on behalf of the organizing committee, welcome you all to the valedictory ceremony of the International Conference on Advanced Materials for Emerging Technologies, ICAMET-23, which we witnessed for last 3 days. I welcome our chief guest, Miss R. Ellis West, Secretary, Directorate of Training and Technical Education, Honorable Vice Chancellor Sir Professor J.P. Saini, Professor Ranjana Jha, who is the conference chair, and Dr. Anurag Gaur, who is the convener of this conference. Now we welcome our chief guest, Ms. R. Ellis West, Secretary, Directorate of Training and Technical Education, and request Dr. Vinamrita to come and present flowers to ma'am. Now I welcome Honorable VC Sir Professor J.P. Saini and request Dr. Dushyant to present flowers to Sir. Thank you, Dr. Dushyant. Now I welcome Professor Ranjana Jha, the chair conference of the chair, and request Dr. Pagin to present flowers to ma'am. Now I welcome Dr. Anurag Gaur, the convener of this conference, and request Dr. Amit to present flowers to Sir. Thank you, Dr. Amit. Now I request Professor Ranjana Jha to felicitate our chief guest, Ms. R. Ellis West, with a memento and shawl. Thank you, ma'am. I request Dr. Anurag Gaur to felicitate Honorable Vice Chancellor, Sir Professor J.P. Saini with the memento and shawl. Thank you. Thank you, sir. As we come to the end of this conference, we have gathered here to reflect on the incredible wealth of knowledge that has been shared over the last 3 days. The time we have spent here has indeed been intellectually very satisfying. We have heard from leading experts in their fields and have been privileged to witness their latest research and advancement in material science and their applications. We have had the opportunity to exchange ideas and network, and hope some of you have been able to forge new collaborations for your future research. Now, I would like to invite Professor Nandlal Singh to present the conference proceeding and report.
Good afternoon to all of you. Now the proceeding started with the conference on the topic International Conference on Advanced Material for Emerging Technology. The theme of the conference is divided in 3 themes. One is the energy storage, materials and devices, functional materials, synthesis and characterization, smarts and biomaterials, and water remedial treatment. These are the themes of the conference. It started with the inaugural function where the NPL Director, Professor Venugopal Achantaji, was the chief guest of the conference. He apprised the audience about the current activities of the CSR, NPL, and the importance of the accurate measurement in the science, being the National Meteorological Institute of the India. Professor A.C. Pandey, Director, International Accelerator Center, he was the guest of honor of the conference, and he stated about the activities going on at the center. He also gave his plenary talk in the later on. And then the dignitary of the university, Honorable Vice Chancellor, Honorable Registrar, HOD, Department of Physics, and conference convener, he have given their own way to about the conference, other things. Now we have having the 3 plenary talk, but unfortunately due to some unavoidable circumstances, one talk would not be materialized by Dr. Rachana Sharma, CSR, CERN, Switzerland. One of the talk given by our director, IUAC, who speak about what is the activities going on the center, and also latest activities on the MRI machine with the superconducting magnets. And also one of the plenary talk given by the Professor Shekhar Mishra. He is working at Fermi National Accelerator Laboratory, USA. He talks about the high energy physics which is being used for the neutrino discovery, and India is also participating in this INO project, which is also in progress in India. And then we have gone through that details about that, and we are having 27 invited talks at different places: CSR, NPL, IPR, Gandhinagar, Delhi University, Delhi Technical University, Chaudhry Charan Singh University, University of Paris, France, Guru Gobind Singh University, JNU, Sabanchi University, Turkey, Jamia Millia Islamia, DRDO, Lucknow and Delhi, Accelerator Center, Delhi, Academic of Sciences and Innovative Research, Ghaziabad, MIT Institute, and the NSUT are also one of the part of this. So many activities at different departments. So these are the activities going on. On the basis of this, we have gone through the different theme-wise presentation and the oral presentation, and the each theme, we have decided to give the best presentation award. So we have 9 oral presentation award in each theme, and there were 2 poster sessions, in which we also decided to have 3 best presentation for the poster. So we have the 6 poster presentation award. So this is all about our conference proceeding of the 3 days. Thank you.
Thank you, sir, for sharing the theme, summary, and analysis of the key highlights. insights that emerged from the conference. Now I would like to invite Professor Ranjana Jha to give the valedictory speech of the conference.
Good afternoon, everyone. I, Ranjana Jha, wholeheartedly welcome our chief guest, Ms. R. Alice Waj, Secretary Technical Education, Delhi Government, our Honorable Vice Chancellor, Professor J.P. Sani, all deans, faculty members, honorable guests, and all the participants to the first international conference ICAMET-23 organized by Department of Physics. As we come to the close of this scientific conference, I feel with both the gratitude and inspiration. It has been an incredible experience to hear from so many brilliant minds, each of whom has contributed to advancing our understanding of the world around us. Over the past 3 days, we have discussed the groundbreaking research, innovative ideas, fascinating insights into a variety of scientific disciplines. We have been challenged to think critically, ask difficult questions, and push the boundaries of our knowledge. As I reflect on this conference, I am struck by the incredible power of collaboration. None of us could have accomplished what we have alone. It is only through the working together, sharing ideas, and building on each other's discoveries that we can make the real progress. I am so grateful for the opportunity to have met and interacted so many of you, and to have formed new connections and friendships that I hope will last for a lifetime. As we leave this conference, we must remember that the work is far from over. There are still so many questions to be answered, so many challenges to be overcome, and so much potential of discovery and growth. We must continue to push ourselves to think creatively, innovatively, to approach problems with an open mind, and to collaborate across the discipline and borders to tackle the most pressing issues facing our world. I have no doubt that the papers and the research work presented here will have a lasting impact on our understanding of the world and will contribute to the betterment of the society in a countless ways. It is up to us to take the lesson learned here and apply them in our own research work. So we should leave this conference with a renewed sense of purpose, a deep appreciation for the power of collaboration, and a commitment to continuing the important work that we have begun here. Thank you all of the organizers, presenters, attendees for making this conference such a memorable and impactful event. I look forward to seeing what we will achieve together in future. Thank you all.
Thank you, ma'am. Thank you for such an energetic speech. We definitely are going to feel void for next couple of days, but then we'll get back to the research with more force. Now I would like to invite Honorable Vice Chancellor, Sir Professor J.P. Sani, to address the audience.
Good afternoon, everyone. Honorable Chief Guest of today's valedictory function, Mrs. Alice was Secretary, Department of Training and Technical Education and Higher Education of NCT of Delhi, Professor Ranjana Jha, Head of the Department of Physics and Chairperson of this conference, wonderful conference, Dr. Anurag Gaur, convener of the international conference, all dean of various faculties, head of the departments, distinguished guests, participants, dear students, ladies and gentlemen. At the outset, let me congratulate Professor Ranjana Jha for her entire team for taking challenge to organize this international conference in time-bound manner on advanced material for emerging technologies in a very short period. And thanks to God for making this environment so pleasant here in the month of May. So this is also here a good time because we were afraid because mostly this time is very hot in the Delhi, but with the grace of God, your conference is successful here in this pleasant environment. I came to know that conference has been organized very successfully in all aspects that include plenary and invited talk by eminent scientists from India and abroad, oral and poster presentations by research scholars from different universities and institutions. We know in 21st century is the witnessing the contemporary technologies with nanotechnology, nanoelectronics, nanosensors, smart materials, biotechnology, bioinformatics, bio-nanotechnology, information technology, optical fiber technology, laser technology, remote sensing, space technology, environment, and gravitation wave, etc., can be quoted as the most important out of large list. Materials engineering shows us how to apply knowledge to make better things and to make things better. Material science and engineering drive innovation in both research and industry in everything from aerospace to medicine. It is fundamental to all other science and engineering disciplines. Modeling and simulation for the development of new and advanced materials and analyzing their properties, performance would definitely dominate in the future, with the special focus on the material for energy and efficiency. The deliberations in the conference covered various aspects of advances in the field of material science and emerging technology. Students would have been benefited with the deliberations of proceedings and will update their knowledge and will improve their skills. Once again, I would like to congratulate Professor Ranjana Jha and whole team for their untiring effort to complete proceedings of the conference successfully. And at the last, I would like to thank our Honorable Secretary of Directorate of Training and Technical Education, Mrs. R. Alice Vaz, for sparing her valuable time here to come and attain the valedictory function of this wonderful conference. So thank you, thanks to everyone. Jai Hind.
Thank you, sir, for your motivating words and your support. We are honored to have with us. Now, I would like to invite Ms. Alice Vaz to give the chief guest address to the audience.
Good afternoon, ladies and gentlemen. Professor J.P. Saini, Honorable Vice Chancellor, Nsut, Professor Ranjana Jha, Head Department of Physics and Conference Chair, Dr. Anurag Gaur, Convener of the conference, and distinguished guests, participants, and students, and ladies and gentlemen. It's a great honor for me to address this August gathering at valedictory function of ICAMET-23. For the last 3 days, you have gone through the different types of new and advanced materials in the form of bulk, nanocomposite nanomaterials, nanostructured thin films, and their applications in various types of sensors and devices. These deliberations will be useful to young researchers to update their knowledge and bring innovation in their research works. As you know that the advanced materials including semiconductors, biomaterials, small materials and nanomaterials which have been designed with a purpose to have a novel and enhanced properties and improve performance over conventional materials in products and processes. As a part of G20 activities, the university is organizing various kinds of conferences and workshops towards empowering the research communities and our Indian economy. I wish all the very best for NSUT and its team for achieving excellence in research field and improve the international standing of our nation. With this note, once again, I thank all of you. Thank you.
Thank you, ma'am, for encouraging the young researchers. Now this is a time to reward the young researchers for the best poster and paper presentations. For that, I will announce the best oral presentations first for the theme Energy Storage Materials and Devices. In this category, we have first best presentation from Ms. Priyanka Maurya. She is from MNIT Allahabad. She is not there. Then we have next presentation from Mimansa Babbar, Civil Department, NSUT, Delhi. I request the dignitaries to present the certificate and memento to the student. Next best presentation is by Gauri IGU Mirpur. Gauri IGU Mirpur. Okay, so in theme 2, which is functional material synthesis and characterization, we have first best presentation by Sunidhi Badola, ACSIR Ghaziabad. Do we have Sunidhi here? No. Then next is KS Anjali, Kurk Institute of Technology, Karnataka. Is she here? Then next is Komal Verma from DTU Delhi. Do we have Komal here? Online. Okay. So we have next theme 3, Smart and Biomaterials. We have first best presentation by Rita Kumari, IG DTU Delhi. Then next is Sonia, NSUT Delhi. Do we have Rita here? No. Yeah, please come forward. Okay. On behalf of Ms. Rita Kumari, ma'am is going to collect her certificate and memento. We have Sonia, NSUT Delhi. Ritu Sharma, Department of Chemistry, NSUT Delhi. Now we have Best Poster Presentation Award. We had posters in 2 sessions. In session 1, we have first award for Deepa Kumari, Department of Physics, NSUT Delhi. Department of Physics, Deepa Kumari. Divya Kaushik, ACSIR Ghaziabad. We have then Manish Kumar Singh, IIT Delhi. Aap Divya Kaushik? Yeah. Divya Kaushik from ACSIR Ghaziabad. Best Poster Award for Session 1. Do we have Manish Kumar here? Then for session 2, Best Poster Award goes to Anant Agrawal, NIT Kurukshetra. Do we have Anant Agrawal? Then Shaili Singh, NSUT Delhi. Next award goes to Chanchal. Chanchal, University of Delhi. A big congratulations to all the awardees. Can we have a big round of applause for all? Now I would like to invite some young researchers for sharing their experience, how was their journey while applying for the conference or while attending the conference. So for that, I would like to invite Miss Manisha from NSUT Department of Physics.
Good afternoon, everyone, all the faculty members and participants present here. I am Manisha, PhD Research Scholar, Department of Physics, NSUT, Delhi. A very well-organized conference, ICAMET-23, a multidisciplinary platform for academics to exchange ideas and research experience on topical issues with practical relevance. It is very helpful for all group of people, researchers, MSc students, and others. It is an appropriate way to flourish and enhance your research network and awareness of different people all over the world. I thoroughly enjoyed all the sessions of the conference. It was very well organized. Most of the presentations were so engaging and very beneficial in respect of recent research in material science. It was a very good experience for me personally, as I received information from diverse domains and feedback for my own PhD work. In many sessions of plenary talks, invited talks, oral presentations, and poster presentations, I got good ideas and further new dimensions for my work in memory devices to improve it and expand it. Apart from research, this conference also helped me in gaining experience during the organization and further confidence in interacting with so many reputed and respectful dignitaries and participants. In addition, the conference is over, but still it will be remembered due to the way it is conducted. I do believe that everyone who had attended and participated in this conference are satisfied with the outcomes of the conference, and this could only become possible because of the organizers who put their best to organize it in the best possible manner. I thank you once again for the efforts exerted and making it one of the memorable events in my research activities. Thank you once again for providing me the opportunity to present my work and having such a grateful experience in such a well-organized and informative conference. Thank you.
Thank you, Manisha. Hope this journey is as memorable as it is for you, for everyone. Now I invite Professor Chaya Ravikant from IGDTU. She will be speaking on her behalf of her student.
Thank you so much, and a very good afternoon, Ms. Alice, Professor Saini, Professor Ranjana, Dr. Anurag. First of all, I would like to congratulate the entire team of ICAMET for the wonderful, wonderful organization of the conference. And we have a similar series of conference at IGDTOW, so I know, being the founder convener of that conference series, I know how much effort goes into organizing such a conference. Endless hours, man hours, get into it, so many discussions and so many efforts are put in as a combined team effort to get to this particular level of the conference. Congratulations, Professor Ranjana from my side, and hope the series goes on. An awesome start by NSUT. Thank you so much.
Thank you, ma'am. Now I invite Dr. Anurag Gaur to share the last vote of thanks.
Good afternoon, our most valued guest, Ms. R. Alice Wedge, Secretary, Technical Education, Honorable Vice Chancellor, Professor J.P. Saini, Professor Ranjana Agrawal, Professor Sanjeev Thakur, all the respected deans, faculty members, invited speakers, delegates, and participants. I feel honored and privileged to get the opportunity to propose a vote of thanks on this great occasion. At the onset, on behalf of the organizing committee, I express our gratitude to Honorable R. Alice Wedge, Ma'am, Secretary Technical Education, Government of Delhi, for having accepted our invitation and graced this function as a chief guest. Ma'am, we are very much thankful to you for being with us today. I would also like to express our gratitude to our Honorable Vice Chancellor, NSUT Delhi, Professor J.P. Saini, who provide us constant support and motivation to organize this event. He has been with us as our leader, mentor, and supported in all possible manner to organize this conference. Sir, we are really fortunate to be led by you, and under your dynamic leadership and guidance, we are very fortunate for this. We are very much thankful for being with us today. My special thanks to the conference chair, Professor Ranjana Jha, for her constant help and guidance that radiated a source of energy within us. At this juncture, I would also like to thank our co-convener of the conference, Dr. Harsh Yadav, for his dedicated efforts to make this conference successful. I would also like to thank all our esteemed deans, delegates, invited speakers who blessed us with their presence and for their valuable knowledge. We will ever remain grateful to you, and we thank you for being with us, and you spare your valuable time during 3 days of this conference. I am also very much thankful to all the program, advisory, and organizing committee members for various help we received towards this conference. Words are not enough to thank their constant guidance and support to shape this conference, and I'm very much thankful to all the faculty members and non-teaching staff of the university in general who always stand by us. I feel proud and thank you for making this event a successful one, and we have been fortunate enough to be backed by a team of very motivated and dedicated students, committee, and volunteers. I cannot thank everyone enough for the involvement they have shown and willingness they have expressed to take on completion of the task beyond their comfort zones. I am also very much thankful to our sponsors, MTech and Gatan Instruments India Private Limited, Casio, Silicom Electronics Private Limited, Anton Power India, Lab India Instrument, SS Scientific Instrument Works, Egg Metals, ABSS, Advent Technology. It would have been impossible to organize this without the support of our sponsors. I would also like to thank Director, CSIR, National Institute of Science, Communication and Policy Research, Professor Ranjana Agrawal, for accepting our request to publish the quality research papers of this conference in the SCI Index Journal, Indian Journal of Engineering and Material Sciences. I would also like to thank to Mrs. Seema Goyal, Deputy Registrar Account, for her help in finance-related work, all the technical staff of this APG complex, Mr. Sanjay Mohan for the media coverage, Mr. Mukesh Garg for beautification and horticulture work, all the cleaning staff, and all those who have supported us in all the ways to make this event successful. Thank you all for making this event successful. Thank you once again.
Thank you, sir. Now we all will rise for national anthem.
जनगण मन अधिनायक जय हे भारत भाग्य विधाता पंजाब सिंध गुजरात मराठा द्राविड़ उत्कल बंगा विंध्य हिमाचल यमुना गंगा उच्चल जलधि तरंगा तव शुभ नामे जागे, तव शुभ आशीष मांगे, गाहे तव जय गाथा। जन गण मंगलदायक जय हे भारत भाग्य विधाता। जय हे जय हे जय हे जय 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 हे।
Thank you everyone. Now we'll go for lunch. Lunch outside the APJ complex. This side. Thank you, ma'am. Sir, lunch. Ma'am.
परवीन जी, ये हमारे स्पॉन्सर हैं ब्रोकर से। ब्रोकर से स्पॉन्सर जो है, कोई हाँ, अरे अभी करते हैं।